NASA is going to the bottom of the ocean to look for alien life, but what they found down there has nothing to do with life, and yet 13,000 feet below the surface of the Pacific, something impossible showed up in the data. This is the story of what NASA actually found at the bottom of the ocean, far above the deepest water on Earth. The world still feels familiar. The sky is open, the light is warm, the surface moves in long, gentle patterns. But beneath that moving skin of the sea, everything begins to change. The blue starts to fade, the warmth disappears, the known world falls quietly away, and somewhere below all sunlight, below every wave, below the reach of storms, ships, and human noise, the ocean becomes something else entirely, not just deep, but ancient, silent, pressurized beyond easy imagination, a world so extreme that for NASA, it does not feel like a part of Earth at all. It feels like rehearsal. Because when scientists at NASA look into the deepest parts of our ocean, they are not only studying this planet, they are studying what might wait beneath the frozen crust of distant moons, where sunlight never enters, where liquid water may still move in darkness, and where, perhaps, something alive has learned to survive without ever seeing a star. That is why this story begins in the ocean, but does not stay there. It stretches outward, into the larger mystery of the cosmos, into the question that has followed science for generations. If life can exist in darkness here, what else may exist in darkness elsewhere? For a long time, the deep sea seemed almost too remote to understand properly. Humans could cross oceans, map coastlines, even step onto the moon. And yet the deepest trenches of Earth remained strangely hidden, as if the planet had folded part of itself away. The ocean floor was not simply far below, it was cut off. No sunlight, no GPS, no easy communication, no room for error. A machine sent downward had to endure crushing pressure, freezing temperatures, and the enormous isolation of a place where rescue was almost impossible. That alone would have made the deep sea one of the hardest environments on Earth to explore. But for NASA, that difficulty was exactly the point, because space is also silent, space is also hostile, space also demands machines that can survive alone, think alone, move carefully through terrain no human can easily reach. And so, in a quiet and fascinating way, the bottom of the ocean became one of the best places on Earth to prepare for worlds beyond Earth. The connection sounds almost impossible at first. A space agency studying the seafloor, a future search for alien life, beginning not in the sky, but in the Hadal dark. And yet the logic is beautifully simple. Some of the most promising places to search for life in our solar system are not dry planets under open skies, but hidden oceans. Oceans sealed beneath ice. Oceans buried in darkness, oceans that may never know sunlight and may not need it. Far from Earth, moons like Europa and Enceladus have become some of the most intriguing targets in planetary science, not because they look welcoming, but because beneath their frozen shells, scientists believe there may be vast bodies of liquid water, and if water exists there, in darkness, under immense pressure, touching rock, warmed by energy from deep below, then those alien oceans may have something in common with the deepest places in our own sea. That possibility changed everything. Suddenly, the ocean floor was no longer just a remote wilderness at the edge of biology. It was a model, a mirror, a living test environment for some of humanity's boldest questions. How do you navigate in total darkness without satellites? How do you send a robot into an environment where direct control is nearly impossible? How do you search for signs of life in a place that does not run on sunlight? And perhaps strangest of all, what happens when the deep ocean begins to reveal things no one expected to find there? Because NASA did not go looking only for strange animals or unusual chemistry or new maps of hidden terrain. It went there to learn how extreme worlds work, how life might survive in them, how machines might move through them, how exploration itself must change when the environment becomes too distant, too dark, too unforgiving for old methods to succeed. And in time, that search led researchers toward a series of discoveries that felt less and less ordinary. Deep ecosystems that lived without the sun, machines learning to navigate like explorers on another world, ancient seafloor landscapes scattered with metallic nodules, and eventually, something that seemed to challenge one of the oldest assumptions in science, something that should not have been there, something that rose quietly inside sealed instruments, in complete darkness, miles below the surface. Oxygen, not where it should be made, not in the way it should be made, but there, waiting in the data, as though the bottom of the ocean had been keeping one more secret in reserve. So tonight, we begin our descent, not in a rush, not as a breaking news story, but slowly, as if we are following a research vessel into black water, watching the last light fade above us, listening to the soft hum of machines built for pressure, and allowing the deep to open layer by layer, question by question, until NASA's journey to the bottom of the ocean becomes something larger than exploration, something quieter, something stranger, a story about Earth, about alien worlds, and about the unsettling possibility that the deepest places are not empty at all, but full of clues. The descent into the deep ocean is not dramatic in the way storms are dramatic. It does not announce itself with noise. It does not arrive in a single moment. Instead, it happens gradually. The light softens first, then it thins, then it begins to feel far away, and as a vehicle sinks deeper through the Pacific, through colder and colder water, the world above starts to seem less like a place and more like a memory. At a few hundred feet, the sea is already dim. At a few thousand, the brightness is nearly gone. And below that, there is only the artificial glow of instruments, the narrow confidence of sensors, the small, fragile awareness of a machine trying to understand where it is in a darkness older than human history. This is the world NASA and deep ocean researchers chose to enter, not because it was easy, but because it was so difficult that success there might teach them how to survive somewhere even more remote. The deepest trenches on Earth are not simply low places on a map. They are wounds in the crust of the planet, long, narrow depressions where one tectonic plate has been forced beneath another, folding the seafloor downward into immense and silent depths. Among them, the Mariana Trench became the most famous. Its deepest point, Challenger Deep, has become a symbol of the unreachable, a place so far below the surface that even now it feels almost mythic. But the Mariana Trench is not alone. Across the Pacific and beyond, other Hadal trenches cut through the planet's outer shell, each one a world of crushing pressure, slow sediment, strange animals, and landscapes that remain only partially seen. These places are not empty. but they are difficult beyond ordinary measure. Pressure builds with every descent. At great depth it becomes so immense that even strong materials can fail without warning. Hulls compress, seals weaken, electronics are pushed toward their limits, and unlike exploration on land, where a broken rover might still be reached, a lost machine in the Hadal zone may be gone forever. That truth shaped everything. For years, deep ocean exploration depended on remarkable engineering, large, expensive vehicles built to endure conditions almost no machine can tolerate for long. They were scientific triumphs, but they were also vulnerable. A single failure could erase years of work and millions of dollars in an instant. That danger became painfully real in one of the most sobering episodes in modern deep-sea research. A vehicle named Nereus had become one of the most important tools ever sent into the Hadal depths. It was designed for extreme exploration, built to descend where very few machines could go, and capable of revealing a world that had remained hidden from science for generations. When it entered the trench, it carried more than cameras and instruments. It carried a certain hope that the deepest ocean could finally become accessible, not just once, but again and again. That the abyss could be studied with continuity. That researchers would no longer have to rely on rare glimpses into the dark. And for a time, that hope seemed justified. Nereus helped produce valuable scientific findings from only a handful of dives. Even limited access to the Hadal zone was enough to expand knowledge, raise new questions, and show just how much of Earth's most extreme environment remained unexplored. But the deep ocean has a way of reminding explorers that it is never fully under control. In 2014, during a dive in the Kermadec Trench near New Zealand, contact with the vehicle was lost. There was no rescue, no recovery, just silence. A machine worth millions of dollars, carrying years of engineering and scientific effort, disappeared into the pressure-darkened water below, gone in an instant. Moments like that change more than mission plans. They change the emotional atmosphere of exploration itself. Because when a machine vanishes in the Hadal deep, what remains is not only technical loss, it is also a confrontation with scale. The trench does not notice what has happened. The darkness remains where it was. The pressure remains what it was. The seafloor continues in silence, as if nothing has been disturbed at all. And above, on the support ship, human beings are left staring into a void they cannot enter, trying to understand how something so advanced could simply be taken. For scientists who had dedicated their lives to these depths, the loss was not just expensive, it was clarifying. The old model of exploration had a flaw built into it. Too much depended on too few vehicles. Too much risk was concentrated in one machine. Too much hope rested on systems so complex and so costly that failure became catastrophic. And in the deep ocean, failure was never hypothetical. It was always waiting. This was the point at which the story began to shift, not away from the trench, but deeper into its lesson. Because sometimes exploration advances not when a method succeeds, but when it breaks so completely that no one can pretend the old approach is good enough anymore. For NASA, and for the scientists working beside NASA, this was not unfamiliar thinking. Space exploration had already taught a similar lesson. When missions depend on one enormous machine, every weakness becomes existential, every malfunction becomes final. But in space, Engineers had begun to imagine another way: smaller systems, cheaper systems, more flexible systems, a philosophy built not around one heroic vehicle, but around many capable ones. And slowly, that same idea began to drift downward, from orbit, into the trenches of Earth. It was a simple thought, but a powerful one. What if the deep sea should not be explored by a single flagship? What if it should be explored the way space is increasingly explored, through smaller, smarter, more affordable machines, each one able to take risks that a $14 million vehicle never could? That question would reshape the future of Hadal exploration. But before the new machines arrived, before the new philosophy took form, there was still the memory of loss, still the image of a vehicle swallowed by pressure, still the recognition that the deepest parts of the planet had not become safer just because humans had learned to visit them. If anything, the opposite was true. The more we learned about the Hadal zone, the clearer it became that this was not a frontier that would yield to confidence alone. It required humility, patience, redundancy, and a willingness to design for failure, because the ocean would not forgive arrogance. Somewhere in that realization, NASA's role in the deep began to sharpen. Not as an outsider visiting an unusual research field, but as a natural partner, because the challenge here was no longer only scientific, it was technological. How do you build machines that can survive isolation, think for themselves, and continue mapping a hostile world even when communication is delayed or absent? How do you create explorers that can endure places where direct human control is impossible? Those are ocean questions, but they are also space questions. And in the darkness below the Pacific, they were beginning to sound almost identical. So the loss of one machine did not end the story. It changed its direction. The trench had made its point. If humanity wanted to keep exploring the deepest ocean, it would need a different kind of vehicle, a different kind of mission, a different kind of courage. And soon, that new idea would take shape in the form of small autonomous machines named for a journey into the underworld. After the loss of Nereus, the silence it left behind did not fade quickly. In deep-sea science, a vanished vehicle is not only remembered as a technical failure, it becomes a kind of turning point, a moment that divides everything into before and after. Before, there had still been a lingering belief that with enough engineering strength, enough money, enough care, perhaps the deepest trenches could gradually be opened using the same old model, one extraordinary machine at a time. After, that belief felt far less certain, because the Hadal zone had exposed a weakness in the strategy itself. One vehicle, one mission, one enormous concentration of cost, risk, and expectation. It was a beautiful approach when it worked, but in an environment where the pressure could crush steel, where communication could vanish without warning, and where recovery was often impossible, beauty was not enough. Something more resilient was needed, something less fragile in its ambition. Among the scientists thinking deeply about this problem was Timothy Shank, a deep-sea biologist whose work had long been tied to the most inaccessible parts of the ocean. For researchers like Shank, the Hadal trenches were not distant abstractions. They were real ecosystems, real biological frontiers, places where animals had evolved under conditions so extreme that every successful expedition felt like a brief visit to another world. And that, in many ways, was exactly the problem. The old vehicles had been built almost like royal processions sent into the abyss. Powerful, impressive, rare. But when one disappeared, the cost was so great that the entire field seemed to pause. It was too much weight for any single machine to carry. Shank began to imagine a different path, a quieter one, a more flexible one. Instead of betting everything on one massive, highly expensive vehicle, what if deep-sea exploration borrowed a lesson from space technology? Not a flagship, but a fleet. Not rare machines that had to survive at all costs, but smaller machines far less expensive, able to work in groups, able to fail without ending the mission. In space exploration, this philosophy had already proven transformative. Small satellites launched in clusters could often do work that once required a single enormous spacecraft. They reduced risk by spreading it out. They made experimentation easier. They allowed engineers to learn faster, adapt faster, and try again without losing an entire generation of progress. This idea had a name in aerospace thinking, the CubeSat philosophy, and slowly, beautifully, it began to make sense for the deep ocean too. If the Hadal zone was too dangerous for one grand machine to carry all hope on its back, then perhaps hope had to be divided, distributed, made lighter, made more numerous, instead of one explorer entering the trench like a solitary hero. There could be several. If one was lost, the mission would not end. If one succeeded, the maps and data could still live on. For a place as unforgiving as the deep ocean, that shift in thinking felt almost revolutionary. And this was where NASA entered the story more fully. Because NASA had spent decades building technologies for environments where direct human guidance was limited, delays were unavoidable, and autonomous decision-making was essential. Space had trained engineers to think this way. How do you build a machine that can keep going when no one can touch it? How do you design a vehicle that can understand where it is, make choices, and protect itself when help is impossibly far away? These questions belonged just as much to the Hadal trenches as they did to Mars, or to any future mission under alien ice. So, the collaboration deepened. Scientists working on the future of trench exploration began partnering with engineers who had built robotic systems for the harshest environments imaginable. Out of that partnership, a new kind of underwater explorer began to take form. It would not be huge. It would not be impossibly expensive. It would not try to dominate the deep through brute force. Instead, it would do something subtler. It would move carefully. It would observe. It would remember. And it would be designed with the understanding that the deep is not conquered by confidence, only entered with humility. The name given to this new machine was Orpheus. It was a fitting name. In Greek myth, Orpheus journeys into the underworld, descending into darkness with purpose, guided not by violence, but by persistence and intention. The Hadal trenches are not the underworld, of course, but to human machinery, they can feel very close. A place of shadow, silence, pressure, and irreversible mistakes. To send Orpheus downward was to acknowledge that the deep was a realm with its own rules, and that entering it required a new kind of explorer. Orpheus was small compared to the grand vehicles that had come before, roughly the size of a motorcycle, far lighter than the older deep ocean platforms, and far less costly to build. That mattered more than it may seem at first, because the reduced cost changed the psychology of exploration. When a vehicle costs a fortune, every mission becomes burdened with fear. Every decision becomes conservative. Every risk feels dangerous, not only scientifically but institutionally. But when a machine is more affordable, experimentation becomes possible again. Engineers can test ideas more boldly. Scientists can imagine fleets instead of singular missions. Failure, while still painful, no longer threatens to erase everything. In that sense, Orpheus was more than a robot. It was a new philosophy made physical, a statement that exploration in the deepest ocean needed to become adaptive rather than monumental. And Orpheus was not alone. Two related vehicles were built, a mythological pair prepared for the dark. Their creation reflected an idea that would become increasingly important in both ocean and planetary science. Memory matters. Not only data, but spatial memory. A machine must not merely descend and survive. It must learn where it is. It must build understanding over time. It must return to places it has seen before and recognize them, the way a traveler remembers a path through a forest, or a rover recalls landmarks on a distant plain. That requirement changed everything about how these vehicles were designed. The deep ocean does not provide GPS. It offers no satellites, no easy reference points, no signal from above telling a machine where it stands. At the bottom of the ocean, an explorer must locate itself by looking outward and inward at once, by watching the seafloor, by tracing patterns, by noticing what remains stable in the dark. NASA engineers already understood this problem well. On Mars, rovers face something similar. They cannot rely on familiar positioning systems. They must use cameras, motion estimates, landmarks, and internal sensing to understand their movement through terrain. And so technology first developed for planetary exploration began to migrate into the oceanic deep. What emerged was not simply a submarine. It was something closer to an autonomous field scientist, a machine that could move through darkness while gradually constructing a memory of the world beneath it. A machine meant not only to visit the trench, but to begin knowing it. This was the deeper meaning of the shift after Nereus. The loss of one vehicle had forced a larger transformation, from singular expeditions to repeatable ones, from fragile ambition to distributed resilience, from heroic descent to patient learning. The trenches had not become less dangerous, but human strategy had become wiser, and in that wisdom, the ocean and space began to overlap more clearly than ever before, because a small robot drifting through the Hadal dark, orienting itself without GPS, mapping an unseen floor, making decisions far from direct control, is already a kind of planetary probe, already a rehearsal, already a preview of what our machines may one day do beneath the ice of Europa, or in the hidden waters of Enceladus. But before those distant futures could be imagined too clearly, Orpheus first had to prove itself here, in Earth's own darkness, in pressure, in black water, in the ancient silence of the ocean floor. And to do that, it would need eyes that could remember. To move through the deep ocean is difficult. To know where you are while moving through it is even harder, because at the bottom of the sea, there are no roads, no stars, no satellites, no horizon, only darkness, rock, sediment, and the small field of vision a machine can create for itself. For humans, that kind of disorientation is hard to imagine. We live among reference points, a road sign, a building, the sun, a shoreline. But the Hadal zone offers almost none of these comforts. A machine must find its own way. This is one reason NASA became such an important part of the story. The problem of deep ocean navigation is not only an ocean problem, it is also a space problem. A robot sent beneath the ice of Europa one day will not have GPS either. It will not be guided every second by human hands. It will have to move in darkness using only its own senses, its own memory, its own judgment. So when NASA engineers helped shape Orpheus, they were not only building for Earth's ocean, they were also preparing for worlds far beyond it. At the center of this new approach was a navigation method called visual inertial odometry. The name sounds technical, but the idea is beautifully simple. The vehicle combines what it sees with what it feels. Its cameras watch the seafloor below. Its internal instruments measure motion, direction, and changes in orientation. Together, these signals allow the machine to estimate where it is and how it is moving. As Orpheus travels above the ocean floor, it looks for features it can remember: a jagged rock, a broken shell, a rough patch of seafloor, a ridge rising from the sediment. These become landmarks, very much like a traveler remembering a road by a bridge, a tree, or a bend in the path. The machine does not ask where it is on a map made by someone else. It begins creating that map for itself. That is what makes this system so remarkable. The deep ocean often has no ready-made map detailed enough to guide a small autonomous explorer. So the vehicle must do two things at once. It must travel through the unknown and slowly teach itself what the unknown looks like. This same broad way of thinking helped NASA on Mars. There too, a machine had to recognize terrain, judge motion, and respond without constant human control. Mars and the deep ocean are very different places, but both deny explorers the ordinary tools of Earth's surface. No GPS, no easy rescue, no room for confusion. That is why the deep sea has become such an important testing ground. It forces technology to prove itself in pressure, darkness, and isolation. And Orpheus was not built only to avoid getting lost, it was built to remember. That memory changes everything. Older deep-sea missions often gave scientists a brief glimpse. A vehicle descended, collected data, and returned. Useful, but temporary. Orpheus was part of a different idea. A machine that could revisit a place and recognize it. A machine that could slowly build continuity from one dive to the next. A map from an earlier mission could become the starting point for a later one. The seafloor could be explored outward in stages. The unknown could become a little less unknown each time, and if multiple vehicles shared this work, the effect would grow even stronger. Maps could be compared, features could be checked again, interesting places could be revisited with greater precision. A fleet could begin to explore the deep, not as isolated machines, but as a connected system. This was the real change after the loss of Nereus. Not just a new robot, but a new philosophy. Exploration through patience, through memory, through smaller machines that could learn instead of simply survive. Orpheus also carried tools for more than mapping. It could search for chemical clues in the water. It could detect signs of hydrothermal vents or cold seeps. And it could gather environmental DNA, tiny traces of genetic material left behind in water and sediment by living things. That meant the vehicle was not only looking at the deep sea, it was listening to it, searching for signs of life even when life itself stayed hidden. That idea matters deeply to NASA, because if we ever send a probe into an alien ocean, it may not find obvious creatures waiting in front of a camera. It may find traces instead. Chemistry, patterns, small signals that something is alive, even if it never fully appears. Orpheus was already practicing that kind of search here on Earth, quietly, carefully, gliding through darkness, making maps, sensing clues, and learning how to explore without direct control. And with every successful dive, one truth became clearer. NASA was not studying the deep ocean by accident. It was doing so because the bottom of our sea may be the closest place on Earth to the hidden oceans of other worlds. Every ridge Orpheus crossed, every patch of seafloor it remembered, every faint chemical signal it detected, brought us one step closer to a future in which a machine may descend beneath alien ice and not be blind. By the time Orpheus began proving itself in the deep, the purpose behind it had become larger than a single machine. This was no longer only about reaching the seafloor. It was about learning how to explore worlds that cannot be explored in ordinary ways. Worlds where communication is slow, where rescue is unlikely, where darkness is complete, and where the environment itself forces a machine to become more independent than any explorer humans had built before. That is why NASA's interest in the ocean floor runs so deep, because far beyond Earth, there are places that may look lifeless from a distance, but may hide oceans below. And among the most fascinating of these places is Europa. Europa is one of Jupiter's moons. From far away, it appears cold, bright, and sealed in ice. Its surface is marked by long fractures and bands, as if the frozen crust has been stretched and broken again and again over immense spans of time. But beneath that shell, scientists believe something extraordinary may exist. A liquid ocean, not a shallow one, not a small hidden reservoir, but a vast global ocean buried beneath miles of ice. An ocean without sunlight, an ocean under immense pressure, an ocean touching rock somewhere far below. And once that possibility is taken seriously, a question begins to rise naturally from it. If Earth's deepest oceans can support life without sunlight, then what might be possible there? This is the connection that changed the meaning of deep-sea exploration. The Hadal zone was no longer just a hard place to study. It became an analog, a rehearsal space, a place where researchers could test not only hardware, but ideas. How do you search for life in darkness? How do you move through a place where no signal from above can guide you? How do you study an environment where chemistry may matter more than light? All of these are ocean questions, and all of them are also Europa questions. There is another moon too, Enceladus, orbiting Saturn, smaller than Europa, but perhaps just as intriguing. Enceladus is famous for something remarkable: giant plumes of water vapor and ice erupting from fractures near its south pole. Those plumes rise out into space, suggesting that beneath the frozen crust, there may also be a hidden ocean, one connected to the rocky interior below. That matters because rock, water, and heat form a very important combination. Again and again, astrobiology returns to these same ingredients. Liquid water, a source of energy, the right chemistry. On Earth, where these conditions come together in darkness, life often finds a way. Not always the kind of life we easily imagine. Not forests or birds or sunlight-fed ecosystems, but microbes, strange animals, entire communities built on chemical energy rather than solar energy. That discovery changed science forever. For a long time, humans assumed life depended ultimately on sunlight, that somewhere, at the base of every ecosystem, there had to be light, but the deep sea taught a more surprising lesson. Life can live by chemistry alone. And once that became clear, alien oceans no longer felt like empty fantasy. They began to feel scientifically possible. NASA did not need the deep ocean to be identical to Europa. It only needed it to be similar in the ways that matter most: darkness, pressure, isolation, autonomy, and the possibility that life, if present, might exist in forms shaped not by sunlight, but by geology. This is why every successful dive by Orpheus carries meaning beyond Earth. When the vehicle learns to navigate without GPS, that matters for future probes under alien ice. When it maps the seafloor and returns to places it has seen before, that matters for robotic memory in remote worlds. When it detects chemical irregularities in the water, that matters for how a future mission might search for subtle biosignatures in another ocean. Even environmental DNA work teaches a broader lesson, not because alien life would necessarily leave DNA exactly like life on Earth, but because it shows how exploration can be based on traces rather than dramatic encounters. A hidden world does not need to reveal everything openly. Sometimes it only offers small hints, a chemical imbalance, a pattern in the water, a signal that something is happening just beyond sight. In that way, the deep sea becomes a teacher. It teaches patience. It teaches indirect observation. It teaches scientists how to search without assuming that life will announce itself in simple, familiar ways. And perhaps most importantly, it teaches humility. Because the search for alien life is not really a search for monsters in the dark, it is a search for systems, for energy flows, for environments where chemistry may quietly support existence. And the bottom of Earth's ocean has become one of the best places to learn how such systems behave. There is a quiet beauty in that. Humans often imagine space exploration as a movement upward, rockets rising, planets circling in the night sky, missions launched toward distant lights. But some of the preparation for those journeys happens in the opposite direction, downward, into black water, into trenches where no sunlight has entered for ages, into environments so remote that they already feel half extraterrestrial. Orpheus was part of that downward preparation, a machine gliding above the seafloor, not only learning about our own planet, but helping engineers imagine how one day a robot might slip through a melted shaft in Europa's ice and enter a sea no eye has ever seen. That day is still far away. The technical challenges remain enormous. A probe designed for an ocean moon would need to be smaller, more radiation-resistant, more self-reliant, and able to survive a journey far beyond anything Orpheus will ever attempt. But the ideas are already forming, and those ideas are being tested here, in our own ocean, in our own darkness. This is what makes the story so compelling. NASA did not go to the bottom of the ocean because it had run out of places to look in space. It went there because the ocean floor may hold the training ground for the next era of exploration. A place where machines can learn to think alone. A place where science can study life without sunlight. A place where Earth begins to resemble the hidden worlds beyond it. And the deeper researchers looked into that resemblance, the more another question began to grow. If the ocean floor on Earth can support life through chemistry alone, then what kinds of life might already be waiting in the dark places of our own sea? To answer that question, scientists had to let go of one of the oldest assumptions in biology, that life depends on sunlight. For most of human history, that idea seemed almost undeniable. Plants grow toward the light, oceans shimmer at the surface, food chains, forests, weather, warmth, all seem to lead back to the sun in one way or another. It was easy to imagine that every living thing, directly or indirectly, belonged to that same bright system. And for a long time, science agreed. The sun was thought to be the great engine of life. Its energy fed plants through photosynthesis. Plants fed animals, animals fed other animals. Even in the ocean, where light fades quickly with depth, the surface world still seemed to govern everything below it. But the deep sea had been keeping another truth hidden, a quieter truth, a stranger one. In 1977, scientists made one of the most important discoveries in modern biology when they found hydrothermal vents on the ocean floor. These were not gentle springs. They were cracks in the seafloor where superheated, mineral-rich water escaped from deep within the earth, miles below the surface, in complete darkness. The seafloor was venting heat and chemistry into the surrounding sea. And around those vents, researchers found something astonishing. Not emptiness, not a lifeless geological curiosity, but thriving ecosystems, dense communities of organisms living where no sunlight had ever reached. It is hard to overstate how shocking this was. Before that moment, the assumption had been simple. No sunlight meant no foundation for life. But here were creatures flourishing in darkness, built around an entirely different energy source. Not photosynthesis, chemosynthesis. In chemosynthesis, microorganisms use chemicals from the earth itself, compounds such as hydrogen sulfide or methane, to produce organic matter. Instead of drawing energy from light, they draw it from chemical reactions. And once microbes can do that, an ecosystem can begin. Small organisms feed on the microbes, larger organisms feed on them. An entire food web rises in the dark, powered not by the sky above, but by the restless geology below. This changed everything. Suddenly, the deep sea was no longer only a place of pressure and mystery. It became proof. Proof that life does not always need the sun. Proof that darkness is not the same thing as death. Proof that water, rock, heat, and chemistry can be enough. For NASA, this discovery mattered far beyond Earth. Because once hydrothermal vent ecosystems were understood, the logic of astrobiology expanded. If life could thrive around vents in Earth's deepest oceans, then perhaps similar life could exist anywhere. Liquid water touches rock and energy flows through the system. An alien ocean did not need sunlight at all. It only needed the right chemistry. That possibility gave the hidden oceans of Europa and Enceladus a new significance. They were no longer just cold bodies of water trapped beneath ice. They became environments that might, at least in principle, support living systems. Not forests, not sunlight-driven worlds, but microbial communities, perhaps clustered around hydrothermal activity. Perhaps feeding on chemical gradients in darkness just as deep-sea organisms do here. The bottom of Earth's ocean had become more than a scientific frontier. It had become a model for thinking about life in the universe. And when researchers returned again and again to the deep, they found more reasons to take that model seriously. Hydrothermal vents were only the beginning. Around those vent systems, life took forms both beautiful and strange. Tube worms, shrimp, mussels, microbes living in dense mats over the rock. Animals adapted not to light, but to chemistry, to gradients of heat, to conditions so unstable and extreme that they seem almost impossible from the surface world. Some creatures gather at the very edge between lethal heat and cold seawater, occupying a narrow strip where survival is possible. Others form symbiotic relationships with bacteria, carrying their chemical partners inside their own bodies. The result is an ecosystem that feels almost alien, and yet it is fully of this earth. This is one reason the deep ocean captures the imagination so powerfully. It does not merely hide unusual creatures, it reveals alternative rules. It shows that life is more flexible, more inventive, more patient than humans once believed. And once those rules become visible, they begin to echo far beyond marine biology. They reshape how we think about Mars, about icy moons, about subsurface oceans, about the possibility that living systems may arise in places once dismissed as hopelessly dark. There is also a quiet emotional shift in this discovery. When humans first looked into the night sky and wondered whether life existed elsewhere, the imagination often turned toward Earth-like worlds, blue skies, mild temperatures, sunlit landscapes. But the deep sea encourages a different vision. Perhaps life in the universe is not always waiting in comfortable places. Perhaps it endures in hidden pockets, under ice, in rock fractures, near chemical vents, in dark oceans buried beneath frozen crusts. If that is true, then searching for life becomes a subtler task. You are no longer scanning only for sunlight and surface water. You are looking for systems of energy, for chemistry, for the quiet signatures of metabolism in darkness. That is exactly why NASA studies Earth's most extreme oceans so carefully. Because every vent field teaches a larger lesson. Every chemosynthetic ecosystem expands the map of what life can be. And every descent into the deep reminds scientists that biology may not care very much about what humans once considered normal. The deep ocean is not a broken version of the surface world. It is its own world, a world with its own logic, its own economies of survival, its own slow and ancient forms of abundance. And perhaps that is why it feels so closely linked to alien oceans. Not because it is identical to them, but because it forces us to imagine life outside the comfort of familiar sunlight. By now, the pattern was becoming clear. NASA's journey into the deep was not only about machines or mapping. It was about understanding the kinds of environments where life might emerge and persist beyond the reach of light. And once that question opened fully, another followed close behind. If life can thrive at hydrothermal vents in complete darkness, what other hidden ecosystems might be waiting across the deep seafloor in colder places, stranger places, places where chemistry still finds a way to feed the living? Hydrothermal vents were the first great shock, but they were not the last. Once scientists understood that life could flourish in total darkness, fed by chemistry rather than sunlight, the deep ocean began to look different, not empty, not simple, but full of hidden possibilities. Because if one kind of strange ecosystem could exist down there, then perhaps others were waiting too, scattered across the seafloor, in forms no one had yet imagined. And that is exactly what researchers began to find. Not all deep ecosystems are built around heat. Some arise in colder places, quieter places, where the seafloor seems still at first glance. No towering vent chimneys, no superheated plumes, only sediment, fault lines, and the slow movement of chemical-rich fluids rising from far below. These are called cold seeps. The name sounds almost gentle, but the environments themselves are no less remarkable. At cold seeps, substances like methane and hydrogen sulfide leak upward through the seabed from buried deposits deep within the earth. They enter the dark ocean floor in silence, and around them life begins to gather. Again, the process starts with microbes, tiny organisms able to use those chemicals as a source of energy. They build organic matter through chemosynthesis, just as vent microbes do, though often in cooler and more stable conditions. And once that microbial base is established, larger life appears: clams, mussels, tube worms, shrimp. Communities arranged not around sunlight, but around invisible chemistry escaping from below. It is one of the most beautiful lessons the deep sea offers. Life does not only adapt to one narrow version of the world, it searches for gradients, for boundaries, for places where energy can be harvested however strange the setting may seem. At cold seeps, the seafloor can appear barren from a distance, long stretches of mud, darkness, silence, and then suddenly, an oasis, a patch of life so dense and unexpected it seems almost painted onto the abyss. For NASA and astrobiologists, places like this are profoundly important because they show that life can build itself not only around hot, dramatic systems like vents, but also around slower, colder chemical environments. That widens the possibilities for alien worlds. A hidden ocean does not need roaring black smokers to sustain biology. It may only need chemical seepage through rock, enough energy for microbes to begin, and enough stability for an ecosystem to form slowly in the dark. Some of the strangest features of cold seep worlds involve methane hydrates. These are ice-like structures formed when methane becomes trapped within lattices of water under high pressure and low temperature. Imagine frozen cages of water holding gas inside them, buried in darkness beneath the waves. To the human mind, they already sound otherworldly. And yet the deep ocean does not stop at strange geology. It adds life. Around methane seeps and hydrates, researchers have found organisms that seem almost dreamlike. Eyeless worms burrowing through the sediment, mussels clustered in dense beds, tube worm colonies rising from the seafloor like pale gardens, all of them existing where no sunlight enters. All of them tied in one way or another to the chemistry of methane and sulfide. Some of these creatures do not feed in the familiar way at all. Instead, they live in partnership with microbes. The bacteria process the chemicals. The animal hosts provide a home. Together, they form a shared system of survival. The animal is not simply eating the environment, it is carrying part of the ecosystem inside itself. That fact alone should be enough to change how we imagine life in the cosmos, because it suggests that survival in extreme environments may depend not on individual organisms acting alone, but on intimate collaborations between species, on biological partnerships shaped by chemistry, pressure, and time. Tube worms are among the best examples. These animals have no mouth in the usual sense, no simple digestive path like the creatures of the surface world. Instead, they rely on symbiotic bacteria living within their tissues. The worms absorb chemicals like hydrogen sulfide and oxygen from the surrounding water and deliver them to the microbes. The microbes, in turn, create organic carbon that nourishes the worms. It is an elegant exchange, a closed loop of chemical life, and it runs entirely without sunlight. That point matters so much because it moves the story away from spectacle and toward principle. The deep ocean is not interesting only because it contains odd creatures. It is interesting because it reveals how life can reorganize itself under completely different rules, different energy sources, different body plans, different relationships between organisms and environment. This is exactly the kind of thinking NASA needs. If life exists elsewhere, it may not resemble the surface ecosystems humans know best. It may be sparse, microbial, collaborative, dependent on chemistry in ways that are easy to overlook if we search only for familiar signs. That is why each new seep community discovered on Earth's seafloor expands more than marine biology. It expands imagination with evidence. It gives science permission to expect the unexpected. And there are many such places. Continental slopes around the world contain methane seeps, hundreds or even thousands of meters below the surface. Wherever scientists have looked carefully, they have often found the same pattern: a dark and seemingly empty plain, interrupted by a concentrated island of life, an oasis in the abyss. That image stays with you because it suggests a different way of thinking about hidden worlds. Perhaps alien oceans are not uniformly alive or uniformly barren. Perhaps they too contain oases, small concentrated zones where chemistry, rock, and water come together just right. And if so, then exploration becomes even more delicate. You are not simply scanning an entire ocean for obvious life. You are searching for rare pockets where the conditions line up, where a seep or vent or fracture creates the narrow opening through which biology can persist. The deep sea has trained scientists to think this way, to stop expecting life to be spread evenly like a blanket, to start looking for clustered abundance in a field of apparent emptiness. That lesson would grow even stranger as research continued, because beyond the seeps and hydrates, deeper into the story, there were environments where the seafloor itself seemed to hold pools of liquid so unusual that almost nothing could live inside them. And yet, even at their edges, life found a way. Beyond the cold seeps and methane hydrates, the deep ocean holds something even stranger. Not just dark water above dark sediment, but actual lakes within the sea, pools of liquid resting on the seafloor, with shorelines, edges, and surfaces of their own. They are called brine pools. And even by the standards of the deep ocean, they feel almost unreal. These pools form where extremely salty water collects in low places on the seabed. Because the salt concentration is so high, the liquid becomes denser than the surrounding seawater and settles into depressions like a heavy, hidden lake. To a passing submersible, the boundary can look almost visible, a shimmering line, a distorted edge, a place where one underwater world gives way to another. But unlike an ordinary lake, this one is toxic to most life. The water inside is often so salty, so chemically extreme, and so low in oxygen that very few organisms can survive within it. In the surface world, such a place might seem barren, another dead zone, another beautiful but lifeless curiosity. Yet the deep ocean tells a different story, because at the edges of these lethal pools, life gathers. Again and again, the same lesson returns. Wherever chemistry creates even a narrow opportunity, living systems begin to organize around it. Brine pools are often associated with ancient geological history. In places like the Gulf of Mexico, thick underground salt deposits were left behind when old seas dried up long ago. Over immense stretches of time, that salt shifted and moved upward through the sediments, opening pathways for brine, methane, and other materials to seep toward the seafloor. The result is a landscape that feels almost impossible: dark ocean above, dense toxic pools below, and around the margins, communities of life feeding not on light but on chemistry. Mussels are among the organisms often found near these edges, so are tube worms and dense microbial populations. The animals themselves are not surviving by some magical resistance to poison. They survive because of partnership, because of microbes capable of converting methane and hydrogen sulfide into usable energy, because of biological systems that have learned how to stand at the border between danger and nourishment. That border matters. Again and again in the deep sea, life appears not in the center of extremity, but at the threshold, at the thin line where conditions are harsh, but not impossible. At the edge between scalding and cold, at the edge between methane-rich seep and barren sediment, at the edge between toxic brine and ordinary seawater. The abyss is full of boundaries, and life, with extraordinary patience, learns how to inhabit them. For NASA, this is more than a marine curiosity. It is another widening of the map, another proof that biology does not need broad, comfortable environments to persist. It can exist in narrow strips, in chemically unusual margins, in places where survival depends on exploiting tiny windows of possibility. That matters deeply when scientists think about extraterrestrial oceans. An alien sea beneath ice may not be filled evenly with life. It may hold isolated zones where chemistry briefly becomes favorable. The habitable parts may be small, localized, difficult to find, and yet still profoundly important. Earth's brine pools help make that possibility feel real. They show that even when an environment seems mostly hostile, its boundaries may host unexpected richness. That idea changes how exploration must work. You cannot only search for broad signs of habitability, you must search for interfaces, gradients, transitions, subtle chemical frontiers where one type of water becomes another, where one energy regime meets another. That is often where the living world quietly takes hold. There is also something almost poetic about these places. A toxic pool in total darkness should feel final, like the end of a story, and yet around it, life arranges itself carefully, elegantly, as if refusing to surrender the terrain entirely. The deep ocean keeps doing this. It keeps showing that life is less fragile and more inventive than surface assumptions would suggest. Not invincible, not everywhere, but astonishingly good at finding narrow opportunities. As researchers continued to explore these deep environments, a pattern became impossible to ignore. Hydrothermal vents, cold seeps, methane hydrates, brine pools, different settings, different chemistries, different temperatures, and yet all connected by one deeper truth. The absence of sunlight does not end biology. It simply changes the rules. This realization had consequences far beyond oceanography. If life can persist in so many chemically powered systems on Earth's seafloor, then the search for life elsewhere must become broader, subtler, and more daring. It must stop asking only where sunlight reaches. It must begin asking where energy moves through rock and water in darkness. That shift is part of what NASA was really finding at the bottom of the ocean, not one single object, Not one dramatic creature, but a new picture of habitability itself, a picture in which life survives through chemistry, partnership, and adaptation. A picture in which dark oceans are no longer empty by default, and once that picture came into focus, another mystery began to emerge, because some of the strangest forms of hidden life were not on the seafloor at all, but beneath it, buried in rock, far below the ordinary ocean, far below sunlight, far below even the deep sea ecosystems that had already transformed science. By this point, the deep ocean had already changed science. It had shown that life could exist without sunlight. It had revealed ecosystems built on chemistry instead of photosynthesis. It had forced researchers to expand the meaning of habitability, and still, the story was not finished, because some of the most unsettling discoveries were waiting even deeper, not on the seafloor, but beneath it. For a long time, humans imagined the boundary of life as something close to the surface, a thin skin of biology spread over the planet, forests above, oceans below, microbes in the soil, creatures moving through water and air. Even when the deep sea entered scientific imagination, it was still mostly thought of as a world on top of rock, not inside it. But slowly, evidence began to suggest something more extraordinary. The planet might be alive much farther down than anyone had expected, in cracks, in fractures, in hidden reservoirs of water sealed within stone. This was not the familiar world of fish, worms, and vent communities. It was something quieter, smaller, more isolated, a biosphere almost entirely out of sight. One of the most striking examples came from deep underground, where scientists studying ancient rock formations found microbial communities living far beneath the surface in water-filled fractures. These were not organisms recently washed down from above. The water itself had been isolated for immense spans of time, tens of millions of years, longer than human civilization, longer than human beings as we know them. And yet within that buried darkness, microbes were alive, not feeding on sunlight, not depending on the surface biosphere, not drawing energy from drifting organic debris that had fallen from above. Instead, they were surviving on chemistry produced within the rock itself. This idea is difficult to absorb at first. Life, sealed away underground for vast periods of time, in hot water, with no meaningful connection to the familiar surface world. It sounds less like ordinary Earth biology and more like a hidden alien system embedded inside the planet. And in a way, that is exactly why it mattered so much. Because if life can persist in such isolation here, then perhaps the range of possible living environments in the universe is even broader than the deep ocean had already suggested. The chemistry behind these subsurface communities is one of the most fascinating parts of the story. Radioactive elements in the surrounding rocks slowly decay. That decay can split water molecules and generate reactive compounds such as hydrogen. Other chemicals, including sulfates, become available in the groundwater. Microbes then use those materials as sources of energy. No sun, no leaves, no photosynthesis, just rock, water, time, and chemistry. A whole system powered by the slow interior processes of a planet. For NASA and astrobiologists, this was another major turning point, because it meant that the search for life on other worlds no longer had to focus only on surfaces, or even oceans. It could extend into subsurface environments, beneath ice, beneath dust, inside fractured rock, Mars suddenly looked different under that light. For years, Mars had attracted attention because of signs that liquid water once flowed on its surface. Ancient river valleys, lake beds, minerals formed in water, all of that suggested a planet that may once have been more hospitable than it is today. But the surface of Mars now is harsh, cold, dry, bombarded by radiation, unfriendly to life as we know it. So the obvious question became, if life ever arose there, where would any remnant of it survive now? The answer, increasingly, seemed to be below the surface, protected from radiation, hidden in rock, possibly feeding on chemical gradients much like Earth's buried microbial systems do. This made the bottom of the ocean part of a larger chain of evidence. Hydrothermal vents had shown that life can thrive without sunlight. Cold seeps and brine systems had shown that chemistry can support ecosystems in many different forms. Now subsurface microbes were showing that life can survive in near total isolation, embedded in the planet itself. The implications were enormous. The universe did not need to provide garden worlds for life. It only needed to provide enough energy, enough chemistry, enough stability for living systems to hold on in darkness. There is something almost humbling about that. Humans tend to imagine life in open landscapes, fields, oceans, skies, visible motion, but much of Earth's living potential may lie in places that never announce themselves so clearly. Inside stone, inside sediment, inside fractures, where water has waited for ages. The planet is stranger than surface intuition suggests, and the more researchers studied these hidden microbial worlds, the more another possibility emerged. Perhaps there are vast forms of biodiversity that remain almost invisible simply because they exist in such small numbers or in places so difficult to sample that science has only barely touched them. This idea led to the concept of a rare biosphere, a deep reservoir of microbial diversity present in low abundance, quiet, overlooked, but immense in variety. Even where a few dominant microbes seem to define an ecosystem, more careful genetic analysis hinted that countless lesser-known organisms were also present. They were not common, they were not obvious, but they were there, perhaps waiting, perhaps forming a kind of biological reserve, a hidden store of possibilities that could become important if conditions changed. That idea gave the deep biosphere an even more mysterious quality. Not just life surviving in darkness, but life maintaining diversity there, keeping options open, holding genetic strategies in reserve. It suggested that even in places of severe limitation, life does not merely endure. It experiments, it prepares, it persists with a subtle richness that may only become visible when science learns how to look more carefully. This matters enormously for NASA's larger question. If life exists elsewhere, especially in isolated or subsurface environments, it may not appear as a broad, thriving biosphere, easy to detect from orbit. It may be sparse, localized, microbial, hidden within rock or sediment. The signs may be faint. The diversity may be concealed, and yet the system could still be real, ancient, and scientifically profound. That is why the deep biosphere changed the story. NASA was not just finding strange environments at the bottom of the ocean, it was finding a whole new way to think about where life might be hiding. Not only in sunlit places, not only in open water, but in darkness, beneath darkness, in buried habitats shaped by chemistry and time. And once scientists began to accept that possibility, another question naturally followed: if life can hide that deeply within Earth. then how much of our own planet is still biologically unexplored? That question has no simple answer. In some ways, Earth is the most familiar place we know. We walk its surface, we map its coastlines, we fly over its mountains and deserts, we watch storms move across it from space. And yet the deeper science looks, the stranger the planet becomes. Because familiarity is not the same thing as understanding. A world can feel known from above, while remaining deeply mysterious below. This is especially true in the ocean. From the surface, the sea often seems like one vast, connected body. But beneath that moving skin lies a layered planet of hidden environments, chemical gradients, pressures, temperatures, and biological strategies that only reveal themselves slowly. Every time researchers descend into those depths, they do not simply confirm what they already suspect. They often find that the ocean has been more inventive than expected. This is one reason the deep biosphere matters so much. It suggests that life is not confined to the obvious, not restricted to visible abundance, not limited to the ecosystems humans can easily observe. There may be entire domains of biology operating quietly beyond ordinary awareness, domains that do not dominate the planet in visible size, but may still contain extraordinary diversity. This was the meaning behind the idea of the rare biosphere. When scientists developed better genetic tools and began looking more carefully at deep microbial communities, they found signs of many organisms present in very low abundance, not dominant, not easy to detect, but consistently there. 100 hidden possibilities where the old view had seen only a few major players. It was as if the microbial world held a reserve library of survival strategies, a hidden archive of forms that did not currently rule the environment, but had not disappeared either. Why were they there? The answer is still uncertain. Perhaps some remain dormant, waiting for conditions to shift. Perhaps others persist in tiny ecological niches, too subtle for us to understand easily. Perhaps deep ecosystems rely on this quiet diversity, the way a forest relies on seeds buried in soil, invisible until the right moment arrives. Whatever the explanation, the lesson is profound. Life may be richer, more layered, and more resilient than surface-level observation suggests. That matters far beyond Earth. Because when NASA thinks about life elsewhere, one of the greatest challenges is not only whether alien life exists, but whether we would recognize it if it did. What if life on another world is sparse? What if it survives in pockets? What if its strongest signal is not abundance, but persistence? The deep biosphere teaches scientists to take those possibilities seriously. A living system does not have to be loud to be real. It does not have to cover a planet to matter. It may whisper through chemistry, through traces, through low abundance communities hidden in rock, sediment, or water. This changes how exploration must be imagined. You are no longer searching only for large, obvious signs. You are searching for subtle structure, for repeated patterns, for anomalies that suggest the environment is doing more than geology alone should allow. That is one reason NASA's work in extreme ocean environments is so important. It trains science to become patient, to gather evidence carefully, to treat faint signals with respect rather than dismissal. The deep ocean is full of faint signals, a trace of methane, a shift in oxygen, a hint of genetic material in water, a microbial population clinging to a fracture in ancient rock. Each clue by itself may seem small, But together, they build a different picture of life, not as something confined to ideal surface conditions, but as something woven into the planet more deeply than humans once imagined. That phrase matters, woven into the planet. Because by now the story had moved beyond isolated marvels. This was no longer just about vent worms, blind shrimp, or microbes in buried water. It was about a new understanding of Earth itself, Earth as a layered living system. Earth as a world whose most profound biological secrets may be hidden in darkness. And if that is true here on the one planet humans know best, then it becomes much harder to assume that other worlds are sterile simply because they appear barren from above. Mars may look empty on the surface. Europa may look sealed and frozen. Enceladus may appear distant and silent. But appearances have become less trustworthy. The deep sea has taught us that. The real story may lie below. This is also why NASA does not only send robots into the ocean, it sends people there too. Not all undersea exploration is about remote vehicles gliding above the abyss. Some of it is about human beings learning how to live, work, and think in environments that resemble space in one crucial way. They separate you from the normal world. They place you inside a small protected habitat surrounded by danger. They demand planning, discipline, and trust in technology. Off the Florida Keys, beneath the surface, sits Aquarius, the world's only permanent undersea research station. It rests beside deep coral reefs and has served as the setting for one of NASA's most unusual training programs. The program is called NEMO, NASA, Extreme Environment Mission Operations. During these missions, astronauts, engineers, and scientists live underwater for days or even weeks at a time. Inside Aquarius, they become aquanauts. And while they are there, the ocean becomes more than an environment. It becomes an analog for spaceflight. The logic is simple and powerful. Underwater habitats are isolated. Movement outside requires preparation and specialized equipment. Tasks must be planned carefully. Resources are limited. Communication and safety procedures matter constantly. In all these ways, the underwater world becomes a rehearsal space for future missions to the Moon, Mars, and beyond. NASA uses this setting to simulate spacewalks, field exploration, and teamwork under pressure. Even gravity can be imitated to a degree by adjusting buoyancy and weighting, allowing researchers to approximate how movement might feel on another world. Again, the direction of preparation is downward. To explore space, NASA goes under the sea. That image captures something essential about this whole story. The bottom of the ocean is not separate from the future of space exploration. It is part of it. A mirror, a classroom, a proving ground. And soon, in one of the most unexpected turns in the entire story, that proving ground would offer something stranger than new training. Stranger than hidden life. Stranger even than alien ocean parallels, because researchers in the deep Pacific were beginning to encounter a signal that should not have existed at all. A rise in oxygen, where oxygen should have been falling. At first, it looked like a mistake, and in science that is often how the strangest discoveries begin, not with certainty, not with celebration, but with suspicion. A reading appears in the data that should not be there, and the first instinct is not wonder, it is doubt. Somewhere in the deep Pacific, on the floor of the Clarion-Clipperton Zone, researchers had placed sealed chambers over patches of seafloor to measure how oxygen behaved in the darkness below. The expectation was simple. Without sunlight and without photosynthesis, oxygen inside those chambers should gradually decline. Microbes and animals consume oxygen. That part was familiar. That part made sense. So if a section of seafloor was sealed off from the surrounding water, the oxygen level inside should slowly fall. Instead, it rose, quietly, persistently, against expectation. Inside the sealed chambers, oxygen concentrations did not drift downward toward depletion. They climbed. At first, the result seemed almost too unreasonable to take seriously. The bottom of an ocean is not a place where oxygen is supposed to be made, at least not in the old picture of the world. Oxygen belongs to sunlight, to green plants, to algae, to cyanobacteria, to all the long biological systems that use light to split water and release oxygen into the environment. That is the story science had told for generations, and it is, in broad terms, a true story. But now, the deep seafloor seemed to be hinting at something else. Not life making oxygen in the light, but oxygen appearing in darkness, miles below the surface, far beyond the reach of the sun. For a while, the easiest explanation was simple instrument failure. Sensors are not sacred. They drift, they malfunction, they misread. In extreme environments, those risks become even greater. Salt water, pressure, temperature shifts, chemical complexity, all of it can create false signals. So when the oxygen readings first seemed impossible, the natural response was to distrust the equipment, not the ocean, the sensors. That choice was entirely reasonable. Science depends on that kind of caution. Extraordinary claims do not begin as accepted truths. They begin by being challenged, repeated, doubted, taken apart. And so the early suspicious readings were not treated as a dramatic breakthrough. They were treated as a possible technical problem, something to be checked, questioned, and perhaps discarded. But the signal did not go away. When researchers returned and measured again using different methods, the pattern remained. Oxygen still rose inside the sealed chambers, not once, not as a random accident, but repeatedly, across many experiments. That is when the mystery deepened. Because once an anomaly survives careful doubt, it becomes harder to ignore. And once it becomes harder to ignore, it begins to change the questions. No longer, why are the sensors wrong? But what in this environment could possibly cause such a result? The Clarion-Clipperton Zone is a vast region of abyssal seafloor in the Pacific Ocean scattered with polymetallic nodules. These nodules lie on the sediment like dark stones, often compared to potatoes or lumps of charcoal. They contain metals such as manganese, nickel, cobalt, copper, and iron. They grow unimaginably slowly, layer by layer, over immense spans of time. To mining companies, they represent a potential resource. To science, they are part of a poorly understood deep-sea world, one already known to host strange life and complex chemistry. Now they seemed connected to something even more unexpected. The oxygen increase was not small enough to dismiss as meaningless noise. In some experiments, it rose far above normal background levels, enough to force a serious reconsideration of what might be happening down there. The first explanation researchers tested was biological. Perhaps deep-sea microbes were producing oxygen through some unknown pathway. That might sound impossible at first, but by now the deep ocean had already taught science not to reject unusual biology too quickly. Researchers knew that some microbial processes can behave in surprising ways, so the idea was worth exploring. But when the team used a treatment meant to kill the relevant microorganisms, the oxygen still increased. That did not prove everything, but it made the purely biological explanation much weaker. If life was not doing it, then what was? The next possibility involved radioactivity. The nodules contain trace radioactive elements, and radioactive decay can split water molecules in a process called radiolysis. Could that be the source? Again, the idea was tested. Again, the numbers did not seem large enough. The modeled contribution was tiny compared to the amount of oxygen being measured, so the puzzle remained. By now, the shape of the mystery had become deeply unsettling. Something in complete darkness, on the seafloor, appeared to be generating oxygen, not through sunlight, not clearly through microbes, not adequately through simple radioactivity. It was the sort of finding that forces science into a slower mood, less triumph, more attention, because this is the point where explanation becomes delicate. One wrong assumption can distort everything. One overlooked mechanism can make the impossible seem real, or the real seem impossible. Still, the data kept pointing in the same direction. There was a source, there was a process, and whatever it was, it challenged one of the oldest boundaries in our thinking about oxygen and life. For NASA, this mattered in a larger way too, because the deep ocean was once again showing that hidden worlds may operate under rules we do not yet fully understand. If even Earth's abyss can still surprise us so profoundly, then how cautious and how open-minded must we be when imagining alien oceans? But before that larger meaning could settle in, the immediate mystery demanded an answer. Researchers had ruled out some explanations, they had narrowed the field, and slowly, attention began turning toward the nodules themselves, those dark metallic stones resting quietly across the abyssal plain. Because perhaps the seafloor was not merely hosting the mystery, perhaps it was building it. The nodules did not look extraordinary at first. That may be part of what makes the story so compelling. Some of the strangest possibilities in science do not arrive in dramatic forms. They arrive as quiet objects, overlooked shapes, things lying in plain sight on the seafloor, while human attention moves past them towards something more obviously alive. Polymetallic nodules are like that, dark, rounded, uneven, scattered across the abyss like forgotten stones. To a camera drifting above them, they can seem almost dull, and yet each one is a record of immense patience. They grow layer by layer over millions of years as metals slowly precipitate from seawater and accumulate around a core. Manganese, nickel, cobalt, copper, iron, tiny additions repeated across unimaginable spans of time. What emerges is not an ordinary rock. It is a slow archive of chemistry, a geological time capsule resting in darkness. For years, these nodules were studied mainly for two reasons. First, because they offered clues about deep-sea geochemistry and the long processes shaping the abyssal plain. Second, because they contain metals that modern industry wants very badly. Nickel and cobalt especially are essential in many battery technologies. That made the Clarion-Clipperton Zone economically interesting long before it became mysterious in a biological sense. But now the nodules seem to be taking on a new significance, not just as mineral resources, not just as seafloor features, but as possible participants in a process that should not have been happening at all. the clue emerged slowly. Researchers began examining the nodules not only as passive objects in the environment but as active electrochemical surfaces. That shift in perspective matters because many things in the natural world do not appear dramatic until you ask the right question about how energy moves through them. A stone may look still, a metal layer may look inert, but if different materials are arranged in the right structure, if electrons can move, if chemical gradients exist, then even something as quiet as a nodule may become part of a dynamic system. This possibility gained clarity through an almost accidental spark of insight. Someone described the nodules as a battery in a rock. At first, it was only a metaphor, a way of speaking about their metal-rich composition, but the phrase stayed in the mind of researchers. What if the comparison was not just poetic? What if the nodules actually behaved in some limited way like natural batteries? To understand why that idea mattered, it helps to think about what a battery really is. A battery stores and separates potential. It creates a difference that allows electrons to flow. That flow can then drive chemical reactions. If something similar were happening in the nodules, even weakly, then perhaps they were not merely sitting on the seafloor. Perhaps they were interacting with the surrounding seawater in a far more active way. Measurements of electrical potential on nodule surfaces suggested this idea was worth taking seriously. The recorded voltages were not as high as a standard household battery, but they were real. Small differences, yes, yet enough to raise a deeper question. Could the layered metals and minerals within the nodules create electrochemical conditions capable of splitting water molecules? Under ordinary circumstances, water electrolysis requires a certain threshold of voltage. A single nodule did not appear to meet that full requirement on its own. But chemistry is rarely as simple as one clean threshold in isolation. Catalysts matter. Surface structures matter, reaction pathways matter, and the nodules contained exactly the sort of metal-rich chemistry that could influence those pathways. Manganese oxides, nickel, complex layered surfaces, defects, and tunnels in mineral structure, all the quiet irregularities that can make a material more chemically interesting than it first appears. So the hypothesis began to form. Perhaps these nodules act as natural geobatteries. Perhaps differences in their layered composition allow electrons to redistribute internally. Perhaps, when in contact with seawater, that electrochemical activity helps split water and produce oxygen. Not sunlight, not biology, not a machine artifact, but rock, chemistry, and the slow logic of mineral structure. If true, it would be one of the strangest discoveries in modern ocean science. Not only because oxygen would be produced in darkness, but because the source would be abiotic, generated without life, generated by the physical properties of seafloor minerals themselves. That idea pushes hard against the familiar story humans tell about oxygen. We are used to treating oxygen as the signature of biology, a gas tied to photosynthesis, to plants and algae and microbial activity under light. And for much of Earth's history, that understanding remains correct. But if nodules can generate oxygen without life, even in localized amounts, then the picture becomes more complex. Oxygen would no longer belong only to the realm of living systems. It would also belong, at least in certain places, to geology. That possibility matters enormously, not because it overturns everything science knows, but because it adds another layer to what hidden worlds may be capable of doing. The deep ocean had already shown that life can thrive without sunlight. Now it seemed to hint that oxygen itself might sometimes emerge without biology. The implications for astrobiology are subtle but profound. If scientists one day detect oxygen or oxygen-related chemistry in an alien environment, they will have to ask harder questions. Is the source biological, geological, electrochemical, some combination of all three? The deep Pacific was once again teaching humility. Signals we think we understand may have multiple origins, and worlds we imagine as simple may turn out to be chemically inventive in ways we barely anticipated. Still, caution remained necessary. The geobattery explanation was a hypothesis, not a final answer. Researchers themselves were careful about that. The oxygen production was not always constant. In many experiments, it slowed after a time. Some scientists wondered whether the reaction depended on the sealed chamber conditions, whether buildup of products or depletion of reactants changed the result. Others asked whether disturbing the seafloor during measurement might expose fresh nodule surfaces that would not normally behave the same way in undisturbed sediment. These were important concerns. Science becomes trustworthy not when it rushes to certainty, but when it keeps its own excitement under discipline. And yet, even with that caution, the mystery had clearly crossed a threshold. The nodules were no longer background objects. They had become central, abyssal stones scattered across the Pacific, perhaps helping create oxygen in total darkness. The thought itself feels almost dreamlike, but the deep ocean has a way of making dreamlike things scientifically serious. And as researchers looked more closely at what those nodules might be doing, another layer of the story emerged, because the nodules were not only part of a chemical mystery, they were also part of a living habitat, one that humans were already considering disturbing on a vast industrial scale. By the time scientists began wondering whether the nodules might behave like natural batteries, another truth had become impossible to ignore. These dark stones were not lying in an empty wasteland. They were part of an ecosystem, a habitat, a foundation for life in one of the least understood places on Earth. From the surface, the Clarion-Clipperton Zone sounds distant and abstract, a huge stretch of Pacific seafloor, remote, silent, hard to imagine. But on the ocean floor, it is a real landscape with structure and meaning. The abyssal plain may look bare from above, yet life there depends on even the smallest stable surfaces. And in many places, the nodules provide exactly that. For some organisms, they are the only hard surfaces in a world made mostly of soft sediment. That matters more than it first seems. In shallow seas, rocks and reefs are common. Creatures can attach themselves easily. But on the deep abyssal plain, much of the ground is soft and shifting. A single hard object becomes precious. It becomes a place to live, a place where small communities can begin. Sponges may attach there. Corals may settle there. Other animals may gather around them for shelter. Over time, a nodule becomes more than a lump of metal-rich stone. It becomes a platform in the dark, a small island of life on a nearly featureless plain. That alone would make the nodules important, but now the story was becoming stranger. If these same nodules were also linked to oxygen-producing chemistry, then their importance would grow even deeper. They would not only support life as habitat, they might also shape the chemistry around them in ways science is only beginning to understand. And that matters because humans have been watching these nodules for another reason. The metals inside them are valuable. Nickel, cobalt, copper, manganese, materials used in batteries and modern technology. To industry, the abyssal plain began to look like a hidden storehouse. That is how deep-sea mining entered the story. From a distance, the logic sounds simple. The nodules sit exposed on the seafloor. They contain useful metals. Why not collect them? But the seafloor is not a warehouse. It is not empty storage waiting to be gathered. It is a living environment, and one we still understand only partially. That uncertainty changes everything. If mining machines remove nodules across wide areas, they do not only remove minerals, they remove habitat, they disturb sediment, they alter a world that forms at an almost unimaginable pace. A single nodule may take millions of years to grow. That means damage done quickly by humans may not be repaired on any meaningful human timescale. For the creatures that depend on those nodules, the loss would not feel temporary. It would feel final. And now the oxygen mystery adds another layer of concern. Because if the nodules really do help produce dark oxygen, then disturbing them on an industrial scale could affect more than visible habitat. It could also change local chemistry, perhaps only a little. Perhaps far more than we expect. Right now, no one can say with full confidence. And that honesty matters. Science does not yet know exactly how widespread the process is, or how important it may be. Does dark oxygen form on undisturbed seafloor? Does sediment cover reduce it? Do nearby organisms benefit from it? Could mining interrupt a process we have only just noticed? These questions remain open. That is what makes this moment so delicate. Researchers are still learning what these nodules truly are. Mineral resources, yes, but also habitat, possibly chemistry in motion, possibly part of a larger abyssal system linking geology and life. For NASA, the lesson goes beyond mining itself. It returns to the same pattern the deep ocean keeps teaching. Hidden worlds are more complicated than they appear. A place that looks barren may be full of life. An object that looks inert may be active. A dark plane that seems empty may hold one of the most important scientific mysteries on Earth. So the nodules began to represent two futures at once. One future saw them as raw material for human technology. The other saw them as ancient parts of a living deep-sea system still teaching us how dark worlds work. And between those two futures stood one difficult question. What if, in trying to take from the bottom of the ocean, we damage one of the strangest environments we have ever found? The deeper scientists looked into the nodules, the stranger the mystery became. For a long time, oxygen had seemed like one of the clearest signals in nature. It belonged to sunlight, to photosynthesis, to the bright surface world of plants, algae, and living systems that use light to split water. That story was so familiar, so deeply accepted, that it shaped the way humans thought about life itself. Oxygen meant biology. Oxygen meant light. Oxygen meant the living world working near the surface of a sunlit planet. But now the deep Pacific was quietly unsettling that picture. Because if the nodules were truly helping generate oxygen in darkness, then oxygen was no longer tied only to life. At least not completely. At least not everywhere. That possibility did not erase biology. It did not undo photosynthesis. But it added something new, something subtle, and unsettling. It suggested that under certain conditions, geology itself might help create a gas we have long treated as one of life's great signatures. That is why researchers moved carefully. The idea was too important to rush, too strange to accept without discipline. And the seafloor is a difficult place to interpret. Every chamber lowered into the abyss changes the environment a little. Every landing stirs sediment. Every measurement captures only a brief moment in a system that may behave differently when left fully undisturbed. So the question became sharper. Was the oxygen being produced naturally on the seafloor all the time, or was the measuring process itself helping trigger the reaction? That distinction mattered enormously. If the process happens continuously in the natural environment, then the nodules may be part of a real abyssal oxygen system. But if it only happens when sediment is disturbed or fresh surfaces are exposed, then the meaning changes. The chemistry would still be fascinating, still important. But the deep sea floor would need to be understood in a different way. This is often how science moves, not from mystery to instant truth, but from mystery to better questions. The first surprise had been the oxygen itself. The next surprise was how many layers of uncertainty stood behind it. How much still depended on reaction pathways, mineral surfaces, sediment cover, water chemistry, and the exact conditions inside those chambers on the seabed. And yet, even uncertainty can be revealing, because once a system proves stranger than expected, it changes the boundaries of future research. Now scientists had to ask harder questions not only about Earth, but about other worlds. If oxygen can form through unusual electrochemical pathways in dark oceans on Earth, then oxygen alone becomes a more complicated signal in astrobiology. A future mission to an alien ocean could not simply detect oxygen and declare life. It would have to ask more. What minerals are present? What chemistry is active? Could the environment itself be generating the signal without biology? The deep ocean was once again acting as a teacher, a patient one, a demanding one, a place where familiar assumptions were not destroyed, but refined, made more careful, made less simple. For NASA, that lesson is priceless. Because the search for alien life depends as much on avoiding false certainty as it does on making discoveries. A misleading signal can shape an entire mission. An oversimplified interpretation can turn geology into mistaken biology. And so the dark oxygen mystery became part of a larger preparation. Not just a puzzle at the bottom of the sea, but a rehearsal in scientific humility. Still, whatever the final mechanism proves to be, one fact remained astonishing. The deepest ocean had produced a phenomenon so unusual that even experienced researchers first struggled to believe it. That alone says something important about how little of the abyss we truly understand. We went down looking for life, chemistry, and better machines, and instead the seafloor offered something stranger. A reminder that even the substances we think we understand best, oxygen, rock, water, can behave in ways that feel almost impossible when placed together in the right hidden world. And perhaps that is the real mood of the deep ocean. Not only mystery, not only darkness, but correction. A place that keeps forcing human knowledge to slow down, to look again, to ask whether the world is simpler than we hoped. Again and again, the answer seems to be no. It is stranger, richer, more layered, and the deeper we go, the more that layered strangeness begins to resemble the questions waiting beyond Earth. Because if our own planet can still surprise us this much, at the bottom of its oldest sea, then what kinds of surprises may be waiting beneath the ice of Europa? Or in the buried oceans of distant moons still turning silently in the dark? By now, the bottom of the ocean had become more than a place of discovery. It had become a mirror. A place where Earth reflects back questions that belong not only to marine science, but to the wider universe. That is one reason NASA keeps returning to the deep. Not because the ocean is merely mysterious, but because it is useful. It allows scientists to test ideas about isolation, pressure, darkness, chemistry, and autonomous exploration in a real environment that already resembles some of the hidden worlds beyond Earth. And of all those hidden worlds, Europa remains one of the most haunting. Beneath its frozen surface, scientists believe there may be a vast global ocean locked under thick ice. No sunlight reaches it, no weather moves across it, no human eye has ever seen it, and yet, if liquid water touches rock there, if heat and chemistry flow through that buried sea, then the logic of the deep ocean begins to matter in a very direct way. Because Earth has already shown what darkness does not prevent. It does not prevent chemistry. It does not prevent ecosystems. It does not necessarily prevent life. That is the lesson hydrothermal vents taught. That is the lesson cold seeps deepened. That is the lesson hidden microbes inside rock fractures made even harder to ignore. Life, at least on Earth, is not loyal to sunlight in the way humans once believed. It is loyal to opportunity, to gradients, to energy, to any place where matter and chemistry allow survival to take hold. This changes the emotional meaning of space exploration. For a long time, people imagined alien life in open landscapes, under skies, near surface water, perhaps on worlds that looked comfortable from a distance, but the deep sea invites another possibility. Perhaps some of the most likely living worlds are not open at all. Perhaps they are sealed, buried, silent. Worlds where life survives not in bright abundance, but in hidden systems nourished by geology. That is why NASA's ocean work matters so deeply. Every time a vehicle like Orpheus maps the seafloor without GPS, that matters for future exploration beneath alien ice. Every time scientists learn how to detect chemical clues without directly seeing life, that matters for future astrobiology. Every time the ocean reveals a process that complicates our assumptions, like dark oxygen, that matters for how carefully we interpret signals on other worlds. The deep ocean is not answering the question of alien life directly, but it is teaching humans how to ask the question better, more carefully, more slowly, with more humility. And perhaps humility is the most important thing of all, because worlds hidden in darkness will not easily reveal their secrets. They will not give simple signals. They will not behave exactly as we expect. The bottom of our own ocean has already made that clear. What looked lifeless turned out to be alive. What looked inert turned out to be chemically active. What seemed familiar turned out to be more complicated than our old stories allowed. That pattern may be true elsewhere too. A frozen moon may look silent from space and still hide an ocean in motion below. A buried sea may look empty and still hold the ingredients for life, or it may hold something stranger still. Environments that teach us new forms of chemistry before they ever teach us biology. This is why the deep ocean matters beyond Earth. It trains imagination with evidence. It keeps science from becoming too narrow. It reminds us that the universe may not repeat the surface conditions humans know best. It may favor hidden places, quiet places, places where life and chemistry unfold in darkness for ages without announcing themselves. So when NASA goes to the bottom of the ocean, it is not only studying Earth, it is studying possibility. The possibility that dark oceans are not dead oceans. The possibility that geology can power systems we once thought required sunlight. The possibility that the strangest environments may turn out to be the most important. And once that possibility settles into the mind, the old image of the universe begins to change. It becomes less empty, less simple, less dependent on bright surfaces and familiar skies. It becomes a universe where life, if it exists elsewhere, may be hidden in the same kind of darkness that covers the deepest trenches of our own sea. And that thought leads us naturally back to the heart of the story. NASA did not only find strange chemistry, it did not only find unusual machines, hidden ecosystems, or surprising signals. What it found at the bottom of the ocean was a new way of thinking, a new way of imagining where life may live, and how carefully humans must search for it. Because sometimes the road to alien worlds does not begin by looking upward. Sometimes it begins by descending slowly into Earth's oldest darkness. And yet, for all the deep ocean has revealed, NASA's story at the bottom of the sea is not really a story of certainty. It is a story of approach, of learning how to enter the unknown without assuming too much too quickly. That may be the deepest connection between ocean science and space exploration. Both fields are forced to work at the edge of human reach. Both depend on machines, patience, and incomplete signals. Both require scientists to build meaning slowly from fragments. A map here, a chemical reading there, a strange organism, a pressure-tolerant robot, an unexpected rise in oxygen inside a sealed chamber. None of these discoveries stands alone. Each one becomes part of a larger pattern. And over time, that pattern begins to say something beautiful and unsettling at once. The universe may be more habitable than humans once imagined, but also more difficult to understand. That tension lives at the center of everything NASA has found in the deep. Take Orpheus, for example, a small autonomous machine moving through darkness using memory and vision to make sense of the seafloor. On one level, it is simply an engineering achievement, but on another, it is something more symbolic. It represents a new kind of explorer, not one that depends on constant human guidance, but one that can enter a hostile world and think carefully for itself. That matters because future exploration, whether in Earth's trenches or beneath alien ice, will depend on exactly that kind of independence. Humans cannot steer every second, they cannot rescue every failure, and they cannot stand physically beside the machine when the environment becomes too extreme. So exploration becomes an act of trust. Trust in design, trust in instruments, trust in slow, disciplined interpretation once the data returns. The same is true of biology. The deep ocean did not reveal life in the forms humans once expected. It revealed life adapted to darkness, chemistry, and isolation. Tube worms nourished by bacteria, shrimp clustering at impossible thermal boundaries, microbes living in buried fractures of rock. Invisible systems powered not by sunlight, but by reactions between water, minerals, heat, and time. These discoveries did not simply add new species to science, They changed the architecture of imagination. They widened the map of where life can belong. And then came the oxygen mystery, perhaps the strangest lesson of all, because it suggested that even the signs we use to interpret life may be more complicated than we thought. Oxygen had long seemed like one of biology's clearest fingerprints. But the abyss forced a new question. What if some signals can come from geology too? What if a dark seafloor can generate effects that resemble biology without being biological? Again, the lesson was not certainty, it was caution. A reminder that discovery means learning not only what to look for, but how not to fool ourselves. This is one reason the deep ocean matters so profoundly to NASA. It is not just a place full of answers. It is a place full of disciplined confusion, a place where science becomes wiser by being surprised. That is rare and valuable. Because one day, if a probe moves through the buried ocean of Europa or samples material from Enceladus, the data it sends back may be just as strange, just as incomplete, just as easy to misread. The deep ocean is preparing humans for that future now, teaching us how to live with ambiguity, how to remain curious without becoming careless, how to keep wonder and skepticism balanced in the same hand. Perhaps that balance is the real thing NASA found at the bottom of the ocean. Not a single object, not one final answer, but a method, a way of thinking shaped by darkness, a way of exploring that accepts uncertainty as part of truth. And that may be more important than any one discovery. Because the greatest scientific journeys rarely begin with certainty, or they begin with a signal that should not exist, a machine that goes where humans cannot, a hidden world that turns out to be alive in unfamiliar ways, and a willingness to keep descending anyway. So the deep ocean remains what it has always been, a frontier. But not the old kind of frontier where humans imagine conquest and closure. This is a quieter frontier, one that resists closure, one that gives knowledge slowly, one that keeps reminding us that the unknown is not empty, only patient. And perhaps that is why the story feels so haunting. NASA went to the bottom of the ocean to prepare for alien worlds. But in doing so, it discovered that Earth itself still behaves like an alien world in places, still capable of surprising us, still capable of hiding systems deeper, stranger, and more delicate than surface life ever suggested. That realization leaves us in a different emotional landscape than where we began, not just impressed by the ocean wall, but humbled by it. Because every descent has revealed the same quiet truth. The deeper we go, the less simple the world becomes. And the less simple the world becomes, the more possible the universe begins to feel. Somewhere in all of this, the story changes shape. It begins as a documentary about NASA, the deep ocean, strange machines, hidden ecosystems, and oxygen where oxygen should not be. But by now it has become something larger, a story about how human knowledge moves, slowly, carefully, often in the wrong direction first, before finding a better one. Because NASA did not go to the bottom of the ocean and find one clean answer waiting in the dark. It found a chain of connected lessons. First, that the deepest parts of Earth are not empty. Then, that life can survive there without sunlight. Then, that machines must become more autonomous if they are to explore such places well. Then, that even geology may produce signals we once assumed belonged only to biology. Each discovery widened the mystery instead of closing it. And perhaps that is why the deep ocean matters so much. It does not simply reward curiosity, it reshapes it. It teaches humans to ask better questions, to stop assuming that familiar surface rules apply everywhere, to stop treating darkness as the end of possibility. For generations, much of science was guided by surface intuition. Life meant light, habitability meant warmth. A promising world was one that looked at least somewhat like the places humans already knew, but the abyss has slowly undone that comfort. It has shown that some of the most important living systems on Earth operate far from the sun. It has shown that chemistry can replace light as the foundation of an ecosystem. It has shown that hidden places may matter more than visible ones. That lesson reaches far beyond oceanography. It changes the emotional center of astrobiology itself, because once you accept that life can persist in darkness on Earth, then the universe stops looking so empty. Not because we suddenly know that alien life exists, we do not, but because the range of plausible living worlds becomes much larger than before. An icy moon is no longer just a frozen object. A buried ocean is no longer just dark water. A subsurface environment is no longer automatically dismissed. The deep sea opened those doors, and NASA has been walking through them ever since. That is why the story of Orpheus matters. That is why the story of hydrothermal vents matters. That is why methane seeps, brine pools, subsurface microbes, and dark oxygen all belong in the same narrative. Together, they form a new picture of reality, a picture in which exploration is not just travel, it is translation, taking one hidden world and using it to learn how another hidden world might work. The bottom of Earth's ocean becomes a language lesson for Europa, a training ground for Enceladus, a discipline of patience for future missions that may one day search beneath alien ice. And this may be the most beautiful part of the whole story. The path to other worlds is not built only in rockets and launch pads. It is also built in dark water, in careful measurements, in robots moving slowly over seafloor sediment, in scientists learning to trust small clues, in the refusal to dismiss a strange signal just because it does not fit the old story. That is how discovery actually works, not as a straight line, but as a gradual surrender of certainty. A willingness to let the world become stranger than expected. NASA went to the bottom of the ocean looking for preparation, analogy, and understanding. What it found was all of that. But it also found a mirror held up to human assumptions, a reminder that Earth itself is not fully known, that some of its deepest systems still resist explanation, that even now, with satellites above and instruments below, there are parts of this planet that answer questions with more questions. And maybe that is not a failure of science, maybe that is its purest form. To keep finding better mysteries, to keep refining the search, to keep descending, because the deep sea does not just challenge technology, it challenges imagination. It asks whether humans are ready to think beyond surface life, surface signals, and surface logic. Whether we are ready to search for life as it may truly be, not only as it appears in the bright world we happen to grow up in. That is the quiet revolution NASA found at the bottom of the ocean, not proof of aliens, not one final object in the dark, but a shift in thought, a widening of the possible. And once that widening begins, it cannot easily be undone. After that, every moon with hidden water feels different. Every buried sea becomes more interesting. Every dark environment becomes a little less silent, because now we know what Earth has already whispered from its deepest places. That darkness is not the end of the story. Sometimes it is where the real story begins. And so the story returns to where it began. Not with certainty, not with triumph, but with a question carried into darkness. What did NASA actually find at the bottom of the ocean? By now, the answer feels both clearer and more mysterious than it did at the start, because NASA did not find just one thing. It found a pattern, a deep pattern running through biology, geology, exploration, and imagination itself. It found that the ocean floor is not merely a remote landscape, it is a proving ground, a place where machines learn how to survive isolation, a place where scientists learn how to read subtle clues, a place where the boundary between the living and the non-living becomes more intricate than surface logic once allowed. That pattern begins with the descent, a fall through fading light into a realm of pressure, cold, and silence. A realm where old exploration methods often fail, where vehicles vanish, where communication breaks, where every successful mission feels less like conquest and more like a respectful visit. It was there that NASA's partnership with deep ocean science began to matter so much, because the challenge was not only to look downward, it was to learn how to move intelligently in a world that gives almost nothing away. That is why Orpheus mattered, not only as a robot, but as a philosophy. Small, patient, autonomous, able to remember the seafloor and return to it. A machine shaped by the same kind of thinking that will one day be needed beneath alien ice. Then came the deeper biological lessons. Hydrothermal vents revealing that life can flourish without sunlight. Cold seeps showing that chemistry alone can nourish rich communities. Brine pools teaching that even toxic boundaries may hold narrow zones of abundance. Subsurface microbes proving that life can persist for immense spans of time in buried darkness, cut off from the world above. Each discovery loosened another old assumption. Each one made the universe feel less dependent on surface conditions and more open to hidden forms of habitability. And then, when even that picture had grown wide and strange enough, the abyss offered one more surprise. Oxygen in darkness. A signal that should not have been there, a possibility that geology itself, under the right conditions, may generate something we long associated mainly with life and light. Whether the final mechanism proves continuous, local, natural, disturbance-driven, or something even more complicated, the lesson has already taken hold. The deep ocean is still capable of overturning certainty, still capable of making experienced scientists pause, doubt, test again, and rethink what they thought they understood. That is not a minor thing. It is one of the most important qualities a frontier can have. To remain genuinely capable of surprise. For NASA, this is why the bottom of the ocean matters so deeply. Because future missions to alien oceans will not enter simple worlds. They will enter worlds of ambiguity, worlds where chemistry may imitate biology, worlds where signs of life may be faint, hidden, local, or difficult to interpret. Worlds where machines must think for themselves and where human understanding must remain humble. Earth's deepest sea is already preparing us for that, not by giving easy answers, but by teaching the discipline of difficult ones. And perhaps That is the real treasure NASA found down there. Not a creature, not an artifact, not a single impossible object in the dark, but a method of seeing, a way of approaching hidden worlds without demanding that they be simple, a way of asking better questions, a way of letting mystery become sharper instead of merely larger. So when people ask what NASA found at the bottom of the ocean, the truest answer may be this. It found that the deepest parts of Earth behave like a doorway between ocean science and space science, between geology and biology, between what we know and what we are only beginning to suspect. And once you stand in that doorway for long enough, the world above begins to feel different too. Less finished, less fully mapped, less certain in its old categories. The sea becomes more than water. The moon becomes more than rock. Darkness becomes more than absence. It becomes potential. And in that sense, NASA's journey to the bottom of the ocean was never only about the ocean. It was about learning how to enter the unknown with patience, with caution, and with wonder still intact. Because the deeper humans go, the stranger the universe becomes. And sometimes the first step toward other worlds is learning how to listen to this one. There is something almost peaceful in that idea, that the search for alien worlds does not always begin with speed or noise or launch fire rising into the sky. Sometimes it begins in silence, in black water, in a machine descending slowly through cold layers of the Pacific, while the last trace of sunlight disappears far above. It begins with patience, with instruments, with questions carried downward into places where humans cannot easily follow. That is the emotional heart of this story. NASA went to the bottom of the ocean because the deep sea is one of the few places on Earth that already feels like another world. It is hostile, remote, difficult to navigate, full of pressure, darkness, and unknowns. And yet it is also alive with hints about how worlds work when sunlight is gone. Hints about how chemistry can replace the familiar comforts of the surface. Hints about how machines may one day survive in places no human being has ever seen. Through Orpheus, NASA found a way to practice autonomy in darkness. Through deep-sea biology, it found proof that life can thrive far beyond the reach of light. Through the strange oxygen mystery, it found another reminder that even the signs we trust most may have more than one origin. And through all of this, the ocean kept giving the same lesson again and again. Look more carefully, assume less. Do not mistake silence for emptiness. That lesson matters not only for science, but for imagination, because the human mind is quick to judge what it cannot see. A dark place feels barren. A frozen moon feels dead. A buried ocean feels unreachable. But the bottom of our own sea has been quietly arguing against those assumptions for decades. It has shown that darkness can hold ecosystems, that pressure can hold life, that hidden worlds are often richer than they first appear. And so, little by little, the universe becomes harder to dismiss. Not because we have found life elsewhere, we have not, but because Earth keeps revealing forms of possibility we were once too limited to expect. That may be the deepest reason NASA studies the ocean floor. Not simply to solve the mysteries below us, but to become worthy of the mysteries beyond us, to train our tools, to sharpen our thinking, to teach ourselves how to recognize life, chemistry, and complexity in places where the old rules no longer apply. This is why the deep ocean feels so haunting. It is both familiar and foreign at once. It belongs to our own planet, and yet behaves like a preview of worlds we have not reached. It is Earth, but also rehearsal. It is science, but also prophecy. A reminder that the future of exploration may depend not on how quickly we move, but on how deeply we learn. So when we ask one last time what NASA actually found at the bottom of the ocean, perhaps the answer is simplest when spoken softly. NASA found that the deepest darkness on Earth is not empty. It found that life can survive without sunlight. It found that machines can learn to move through hidden worlds. It found that rock, chemistry, water, and time can combine in ways that still surprise us. And above all, it found that the bottom of the ocean is not the end of the map. It is the beginning of another one, a map that stretches from Pacific trenches to buried oceans under alien ice. A map drawn not in certainty, but in curiosity. Not in conquest, but in careful return. And maybe that is the most beautiful ending this story can offer, that even now, in an age of satellites and sensors and powerful machines, the world still keeps some of its greatest truths in darkness, waiting patiently for those willing to descend slowly enough to notice them. And perhaps that is where this journey should rest, not in a final answer, but in a final feeling. A feeling that the world is deeper than it appears, stranger than it appears, more alive, more layered, and more mysterious than the surface ever suggests. The ocean taught that lesson first. Long before NASA entered the story, the deep sea was already waiting below with its ancient silence, its hidden pressure, its impossible distances, and its quiet refusal to become simple. But when NASA came down into that darkness, bringing its machines, its questions, and its search for analogues to alien worlds, the meaning of the deep began to widen. The bottom of the ocean was no longer only an oceanographic frontier. It became a cosmic one. A place where Earth begins to resemble the buried oceans of Europa, a place where hidden chemistry begins to resemble the possibilities of Enceladus, a place where the search for life stops depending on sunlight and starts depending on patience. That is what makes this story feel so unusual. It is not really about one expedition, not one vehicle, not one experiment, not even one discovery. It is about a gradual transformation in the human view of life itself. At first, we imagined life as something tied to warmth, light, and open surfaces. Then the deep ocean showed us something else. It showed us ecosystems built on chemistry, worlds inside darkness, communities surviving where old biology once assumed nothing could live. Then came the machines, learning to descend, map, remember, and navigate without GPS. Then came the nodules, silent stones that may be doing more than simply resting on the abyssal plain. Then came the realization that the deepest ocean was not only full of strange life, but full of strange rules. And that may be the most important thing NASA found, not only hidden ecosystems, but hidden rules. Rules about survival, rules about energy, rules about where chemistry can lead when light is gone. Those rules matter, because the universe may be governed by them in far more places than we once believed. If a moon beneath ice holds liquid water, if rock and heat meet in darkness, if chemistry moves through cracks and boundaries the way it does here, then life, or something close to life, may not be as rare as surface thinking once suggested. Still, the deep ocean leaves us with humility, not certainty. We do not know what waits beneath alien ice. We do not know whether Europa or Enceladus truly hold living systems. We do not know whether Mars still shelters chemistry that once belonged to life. But we know this: Earth has already shown that hidden worlds can be far more active than they appear. It has shown that darkness is not the end of habitability. It has shown that strange signals deserve patience before judgment. It has shown that the unknown often becomes more complicated, not less, when studied carefully. That is why the bottom of the ocean matters so much, because it trains us for a future in which the greatest discoveries may arrive quietly, not as obvious creatures in front of a camera, but as subtle patterns. A rise in oxygen, a chemical imbalance, a hidden ecosystem where none should exist, a machine returning with data that forces science to slow down and think again. Those are the real sounds of discovery, soft sounds, measured sounds, the sounds of certainty being loosened, and maybe that is why this story belongs so naturally in a documentary for sleep, because the deep ocean does not reveal itself through noise, it reveals itself through stillness, through repetition, through long attention, through the calm acceptance that some truths arrive only when we stop rushing past them. Tonight, we followed NASA downward into one of the darkest places on Earth. We followed the loss of machines and the building of new ones. We followed life beyond sunlight. We followed chemistry into places where biology and geology begin to blur. We followed questions all the way to the edge of alien oceans. And in the end, what we found was not a closing statement, it was an opening in thought, an opening in possibility, an opening in the long human imagination of where life may dwell. So let the ocean rest now beneath us, cold, black, patient, its trenches holding their pressure, its nodules lying quietly on the plain, its hidden ecosystems breathing in darkness, and somewhere far beyond, let the frozen moons continue turning through space. Silent, too, waiting for the day when one of our machines may finally reach them. Until then, the bottom of Earth's ocean remains our nearest rehearsal, our nearest mirror, our nearest whisper from another kind of world. And maybe that is enough for now, to know that the deep is still there, still teaching, still asking better questions than we came with, and still reminding us, in the gentlest possible way, that the universe may be full of hidden oceans, and that hidden oceans may be full of far more than silence. And after all of that, the final mystery may not be what NASA found below, but what the deep ocean changed above. Because once you have followed this story far enough, once you have descended through the fading light, past the lost machines, past the silent trenches, past the ecosystems that live without the sun, past the nodules that may create oxygen in darkness, the world does not feel quite the same when you return. The surface still shines, the sky still opens, the ordinary world still moves with its usual speed. But somewhere underneath that familiar brightness, another image remains, a darker Earth, a quieter Earth, a planet whose deepest places are still asking questions science cannot fully answer. That may be the real gift of the deep ocean. Not that it gives us certainty, but that it keeps us awake to wonder. NASA entered that darkness looking for preparation. Preparation for alien oceans. Preparation for distant missions. Preparation for the possibility that one day A machine may descend beneath frozen ice on another world and begin searching for life where no sunlight has ever reached. And yes, the deep ocean offered that preparation. It taught engineers how to build machines that can move without GPS. It taught scientists how to search for chemical clues without expecting simple answers. It taught explorers how to trust slow data, incomplete signals, and the patient logic of hidden systems. But the ocean offered something else too: perspective. A reminder that the line between Earth science and space science is thinner than it seems. Because sometimes, to understand another world, we must first learn how little we understand this one. That is what makes the story feel so calm and so haunting at the same time. The deepest ocean is not loud. It does not rush to impress us. It does not reveal itself all at once. It waits. It lets questions gather slowly. It lets discoveries arrive one careful layer at a time. And maybe that is why it feels so connected to sleep, to dreaming, to the soft edge between what is known and what is only beginning to appear. The deep sea is full of darkness, but it is not empty darkness. It is full of systems, of memory, of chemistry, of life in forms that surface thinking once failed to imagine. And through NASA's descent into that world, we are left with a final, quiet understanding that hidden places matter, that the unseen may be more important than the visible, that the future of discovery may depend not on how boldly we claim to know, but on how gently we are willing to keep looking. So let the ocean grow still again. Let the trenches rest beneath their miles of water. Let Orpheus and all the machines that followed continue their slow work in darkness. Let the nodules lie quietly on the abyssal plain, ancient, patient, unresolved. Let the hidden microbes remain in their buried fractures of rock. Let the vents continue releasing heat into black water. Let the cold seeps feed their quiet oases, and far away let Europa and Enceladus keep their secrets a little longer. Because now we know enough to understand that their silence does not mean emptiness. It may only mean distance. For now, NASA's path to those worlds still passes through our own, through Earth's deepest sea, through the lessons of pressure, isolation, darkness, and wonder. And perhaps that is the softest truth this story leaves behind, that sometimes the way forward is downward. Sometimes the road to alien oceans begins with the ocean beneath our own sky. Sometimes the search for life elsewhere begins by noticing how strange life already is here. And sometimes the greatest discovery is not an answer at all, but the realization that the universe has become larger, deeper, and more possible than it was before we started looking. So tonight, as this descent comes to rest, leave the ocean there in your mind. Vast, black, quiet, ancient, a hidden world beneath the world, and somewhere inside that darkness, still waiting, still teaching, still alive with questions. And so at last we rise slowly, gently, as if returning from a world that never fully belonged to us. Far below, the trenches remain exactly where we left them. The seafloor remains cold. The pressure remains enormous. The nodules remain scattered across the abyssal plain, dark and patient. The hidden ecosystems continue their silent work. The vents still release their heat. The seeps still feed their strange communities, and somewhere in that darkness, the unanswered questions remain alive. That may be the most honest ending possible, because the deep ocean does not offer a neat conclusion, it offers continuation. It tells us that discovery is still happening, that the bottom of the sea is not a solved place, not a finished map, not a closed book. It is still becoming known, one descent at a time. NASA went there to prepare for other worlds, to test machines, to study extreme environments, to learn how life and chemistry behave when sunlight is gone, and in doing so, it found something more enduring than a single result. It found a new relationship between Earth and the cosmos. The deep ocean became a bridge between marine biology and astrobiology, between the pressure of the Hadal zone and the hidden oceans beneath alien ice, between the old idea that life belongs to light and the newer, stranger idea that life may belong wherever energy quietly moves through darkness. That bridge matters, because one day, perhaps decades from now, a machine may descend into an ocean on another world. It may slip beneath ice no sunlight has ever crossed. It may move through black water older than human history. It may search for chemistry, for gradients, for traces, for some whisper that life has found a way there too. And when that day comes, the path to that moment will not begin only in laboratories or launch sites. Part of that path will lead back here, to Earth's deepest ocean, to the lost vehicles, to the patient robots that learned to navigate in darkness, to the hydrothermal vents and the cold seeps, to the buried microbes, to the strange oxygen rising where it should not have risen, to every lesson the abyss gave us when we were humble enough to notice it. Until then, the ocean remains our nearest hidden world, our nearest rehearsal, our nearest proof that darkness does not mean emptiness, and perhaps that is enough to rest with tonight. Not certainty, not a final answer, but a quiet expansion of possibility, a sense that the universe may be richer than it appears, that life may be more adaptable than we once believed, that our own planet still holds places strange enough to prepare us for worlds we have not yet touched. So let the last image be simple: a research vessel floating above black Pacific water, night overhead, silence below, and somewhere, far beneath the hull, a machine drifting over the sea floor, watching, measuring, remembering. While Earth, and in one of its deepest and oldest places, continues teaching us how to search the darkness. And with that, we let the ocean close again, softly, patiently, keeping its pressure, keeping its silence, keeping its ancient questions for the next descent. Even now, after all these descents, after all these machines, after all these measurements taken in darkness, the bottom of the ocean still feels unfinished. That may be why it stays in the mind so long. Not because it gives clear answers, but because it refuses to become ordinary. The deep sea remains one of the last places on Earth where modern science still meets something close to true vastness. Not just physical vastness, but conceptual vastness. A place where biology, geology, chemistry, and exploration keep crossing into one another until the old boundaries begin to blur. NASA entered that world looking for preparation, and it found preparation, yes, but it also found perspective. A reminder that hidden worlds are rarely simple, that life, if it exists elsewhere, may not arrive in forms that are easy to recognize, that even oxygen, one of the most familiar substances in our story of life, may behave in ways that require caution before interpretation. This is what the ocean taught most clearly. Not that every mystery has an answer ready and waiting, but that the unknown deserves patience, The Hadal zone deserves patience. The seafloor nodules deserve patience. The strange ecosystems living without sunlight deserve patience. And the buried oceans of Europa and Enceladus, if we ever reach them, will deserve even more. Because the search for life is not only a search for presence, it is also a search for meaning. If we detect a chemical signal, what does it mean? If we find oxygen, what does it mean? If we discover a pattern in water chemistry, in rock, in frozen plumes, in hidden gradients beneath ice, how do we know whether it belongs to biology, geology, or some boundary between the two that we do not yet fully understand? The deep ocean has already shown that such boundaries are real, and that is why NASA keeps looking downward with such seriousness. The ocean is not only a place of analogies, it is a place of discipline, a place where science learns how to ask stronger questions before it carries those questions to another world. That may be one of the quietest and most powerful forms of preparation there is, not merely building better machines, but building better judgment. Orpheus was part of that. A small autonomous explorer learning to move through darkness without GPS. Learning to recognize the seafloor by memory. Learning how to search, not with haste, but with care. And in a way, Orpheus becomes a symbol for this whole story, an explorer of hidden spaces, a guide through pressure and silence, a machine that does not conquer the deep, but listens to it. That same attitude appears everywhere, in the science, in the vent studies, in the seep studies, in the work on buried microbes, in the effort to understand dark oxygen without forcing the mystery into a conclusion too quickly. Again and again. The ocean asks for the same thing: attention, slow attention, careful return, willingness to doubt what seems obvious, willingness to test what seems impossible. That is how the deepest truths often appear, not in noise, not in spectacle, but in a pattern that repeats long enough for humans to stop dismissing it. And maybe that is the reason this story belongs so naturally in the dark. Because it is a story about places where certainty fades the way sunlight fades in the sea. A story about what remains when brightness disappears, chemistry remains, pressure remains, memory remains, questions remain. And sometimes life remains too, far below the surface, beyond the old boundaries of expectation. That is what makes the ocean such a profound teacher for NASA. It does not merely resemble alien worlds in appearance, it resembles them in difficulty, in ambiguity, in the way it forces explorers to work through fragments and clues rather than complete understanding. And perhaps that is the most honest preparation humans can have for the future. Not confidence that we already know what we will find, but experience in meeting worlds that refuse to be simple. So the bottom of the ocean stays with us, not as a solved mystery, but as a living one, a place where every descent sharpens the next question, a place where the hidden parts of Earth keep widening the meaning of life, habitability, and exploration itself. And as long as that remains true, the deep sea will not only be part of our planet, it will remain part of our future. And perhaps that is where the deepest change has happened, not only in the data, not only in the machines, but in the human imagination itself. Because once the deep ocean has shown you enough, once it has revealed life without sunlight, chemistry without easy explanation, and hidden systems operating far below the surface world, it becomes difficult to look at the universe in the old way again. Before discoveries like these, it was easier to imagine life as something delicate and narrow, something that needed just the right surface, the right warmth, the right light, something bound to familiar conditions. But the bottom of the ocean kept loosening those old ideas. It kept showing that life is more flexible than expected, that worlds can be active where they look silent, that darkness can be full of structure, that hidden places may matter more than visible ones. This is why NASA's work in the deep carries such emotional weight. It is not just technical preparation, it is philosophical preparation, a training of the mind, a slow adjustment of expectation. The universe may not present life in comfortable, surface-level forms. It may hide it, bury it, scatter it in rare pockets, support it through chemistry instead of sunlight. And if that is true, then the search for life becomes a quieter kind of search, less about dramatic revelations, more about subtle patterns, more about patience, more about knowing how to listen when a world speaks softly. The deep sea has taught exactly that, a rise in oxygen where oxygen should not rise, microbes in rock where life should not last, vent communities where sunlight never enters, cold seeps nourishing life in slow chemical silence. Again and again, the lesson is the same. The world is under no obligation to match our first assumptions. That may be the most valuable thing NASA found at the bottom of the ocean. A reason to expect surprise, a reason to remain humble, a reason to believe that the hidden parts of planets and moons may deserve more attention than their surfaces alone. And this changes how future exploration must be imagined. One day, when a probe moves through alien ice or samples a plume from a distant moon, scientists will need more than instruments. They will need discipline. They will need caution. They will need the ability to separate wonder from haste. Because a strange signal is not enough. It must be tested, repeated, questioned, placed in context. The ocean has already been training us for that, training us to recognize that geology can imitate biology, that life may exist in forms far less obvious than surface creatures and green landscapes, that the most important discovery may begin as something almost easy to dismiss, a small anomaly, a weak signal, a reading that seems wrong until it appears again. This is how hidden worlds introduce themselves, not with certainty, but with persistence. So perhaps NASA did not simply find strange things at the bottom of the ocean. Perhaps it found a new relationship with uncertainty itself. A better way to stand inside mystery without rushing to close it. A way of exploring that keeps wonder alive, while still demanding evidence. That balance may be the true bridge between the ocean and space, because both are places where humans must learn to live with distance, with incomplete knowledge, with environments that reveal themselves only in fragments, and in both places, the future belongs not to those who assume too much, but to those who can keep looking carefully for a very long time. The deep ocean remains that kind of place, a patient frontier, a silent teacher, a dark world beneath our own, still quietly reshaping the way we think about life, about planets, and about what may be waiting in the hidden waters of the cosmos. And maybe that is enough for now. Not a final answer, but a wiser question, not certainty, but readiness. Readiness for the day when another descent begins, not into the Pacific, but into an ocean no human story has ever touched before. And when that future descent finally comes, if it comes, it will not begin in total darkness. It will begin with memory, with everything the deep ocean has already taught us, with every failed vehicle, every careful return, every strange ecosystem, every chemical signal that forced scientists to slow down and think again. That is the quiet legacy of NASA's work at the bottom of the ocean. Not just data, but preparation, written into method, preparation written into caution, preparation written into the growing understanding that hidden worlds must be approached gently, because they often reveal themselves only a little at a time. The deep sea has shown this again and again. At first, humans imagined the abyss as emptiness. Then it became a place of extreme life. Then it became a place where geology and biology seemed to overlap in unexpected ways. Then it became a training ground for machines meant to think for themselves. Each layer changed the story. Each layer asked for a new level of patience, and perhaps that is why the bottom of the ocean feels so powerful in the imagination. It does not simply hide things, it changes the meaning of what is hidden. A trench is not just a deep place, it is a boundary in thought. A vent is not just hot water escaping rock. It is evidence that energy can support life where sunlight never arrives. A nodule is not just a mineral deposit. It may be habitat. It may be chemistry in motion. It may be part of a system we are only beginning to understand. The ocean keeps doing this. It keeps taking things that seem simple from far away and making them more complicated up close. That lesson matters enormously for the future, because the same will likely be true of other worlds, Europa, Enceladus, perhaps even hidden environments on Mars. None of them will surrender their meanings easily. A single reading will not be enough. A single photograph will not be enough. A single chemical clue will not be enough. The path forward will demand repeated measurements, careful interpretation, and the humility to admit how much remains uncertain. Earth's deepest sea has already been teaching that discipline. That may be why NASA belongs in this story so naturally. A space agency studying the seafloor can sound strange at first, but in truth, it makes perfect sense. Because the challenge is the same in both directions. How do you explore a place humans cannot easily enter? How do you guide machines through darkness and delay? How do you search for life without assuming it will look familiar? How do you interpret signals in environments that may be more inventive than your theories? Those are ocean questions. They are also planetary questions. And that is why the bottom of the ocean has become something more than a scientific destination. It has become a rehearsal for contact with the unknown. Not contact in the dramatic sense, not a meeting with obvious creatures in the dark, but contact with systems, with hidden order, with forms of activity that force human thought to widen. That widening may be the most important discovery of all, because once the imagination expands, science can follow it with better tools, better missions, and better questions. The deep ocean has already done that work. It has taught us that silence is not emptiness, that darkness is not inactivity, that hidden environments may hold some of the most important answers in nature. And it has also taught something softer, but equally important, that the search itself must remain calm, careful, patient. The abyss does not reward haste, it rewards attention. So perhaps this is the final gift the ocean gives to NASA. a certain kind of scientific temperament, one suited not only to trenches and seafloor plains, but to icy moons. Is buried oceans and distant worlds still waiting beyond the reach of today's machines? A temperament willing to descend slowly, to observe closely, and to let mystery remain mystery until evidence is strong enough to change it into knowledge. That is a rare kind of strength, and it may be exactly the strength humans will need most when the next hidden ocean finally opens before us. Until that day arrives, the deepest ocean remains our nearest unknown, not because it is the only unknown left on Earth, but because it is one of the few places where the old feeling of discovery still survives, almost untouched. There is still pressure there that can crush our machines. Still darkness that can erase direction, still chemistry that behaves in unfamiliar ways. Still ecosystems that make surface life feel like only one version of a much larger biological story. That is why this journey lingers, because NASA did not go to the bottom of the ocean and return with a single treasure. It returned with a changed horizon. A wider sense of what worlds can be, of what life can be, of how carefully humans must move when they enter places built on silence, depth, and time. The deep sea gave lesson after lesson. It taught that exploration cannot depend only on strength. Nereus showed that. One powerful machine, one catastrophic loss, and an entire model of discovery had to be reimagined. Then Orpheus arrived with a different philosophy, smaller, smarter, more adaptive, a machine designed not to dominate the abyss, but to learn from it. That shift mattered, because the future of exploration on Earth and beyond may belong less to heroic singular missions and more to patient, distributed intelligence. Then came the biology. Hydrothermal vents shattered the old belief that sunlight stood behind every living system. Cold seeps widened the idea further. Brine pools showed that even lethal environments may hold narrow borders of abundance. Buried microbes proved that life can endure in darkness deeper than the ocean floor itself. Each new discovery loosened another ancient certainty. And then, almost impossibly, came oxygen in the dark. Not confirmed as a final mechanism, not yet fully explained, but enough to remind science that the abyss still contains processes capable of unsettling its most familiar assumptions. Taken together, these are not separate curiosities. They are connected lessons, lessons about hidden worlds, about subtle energy, about signals that must be interpreted carefully, about the long patience required to study places where biology and geology may overlap in ways that blur the lines between them. This is exactly why the bottom of the ocean matters to NASA, because any future search for life beyond Earth will face the same challenge. The challenge will not only be to find something strange, it will be to understand what the strangeness means. A chemical trace may suggest metabolism or mineral reactions. A gas may suggest life or geology. A pattern may look familiar until deeper study reveals an origin no one expected. Earth's deep ocean is already training us for that complexity. It is teaching us how to search without oversimplifying, how to interpret without rushing, how to let a hidden world remain strange long enough for the right explanation to emerge. Perhaps that is the quiet greatness of this story. It does not end with mastery, it ends with readiness. Readiness for better machines, better questions, better forms of caution, and better forms of wonder. Because wonder alone is not enough. Wonder must be disciplined. That is what the abyss teaches. To remain open, but exacting. To remain curious, but patient. To keep descending, while resisting the urge to decide too quickly what the darkness means. And maybe that is why the bottom of the ocean feels so deeply connected to the future. It is not just a place we study, it is a place that shapes us back. It reshapes engineering, it reshapes biology, it reshapes the imagination of what might be alive in the universe. So let the ocean remain there now, vast beneath thought, a black world under the world, its trenches still holding their pressure, its nodules still resting across the plain, its hidden life still moving through chemistry and silence, and somewhere beyond Earth, let the frozen moons continue turning in darkness too, waiting for the slow intelligence we are still learning here. Because before humanity can truly enter another hidden ocean, it must first become the kind of species that knows how to enter one gently. And perhaps that is the final image this story leaves behind. Not a monster in the dark, not a single revelation waiting at the bottom, but a species learning. It's very slowly how to approach hidden worlds with the humility they require. Because that is what NASA truly found at the bottom of the ocean. Not only vents, not only strange shrimp and buried microbes, not only nodules that may help create oxygen where oxygen should not be, not only robots learning to move through darkness without GPS, it found a different scale of thinking, a slower scale, a deeper one shaped by pressure, silence, and the realization that the unknown does not always reveal itself in dramatic ways. Sometimes it appears as a small signal rising in the data, a tiny chemical imbalance, a machine returning with a better map than before, a patch of life in a place once thought barren, a question that grows more powerful the longer it refuses to disappear. That is how the ocean speaks, quietly, indirectly, patiently, and perhaps that is why it has become such a powerful rehearsal for space, because distant worlds will almost certainly speak the same way. If there is life beneath alien ice, it may not greet us openly, it may whisper through chemistry. If there are active systems in a buried ocean, they may first appear as gradients, patterns, and anomalies. If a future machine finds something profound on Europa or Enceladus, the first sign may be so subtle that it looks almost unimportant. The deep ocean has already trained us to respect those subtle signs. That may be one of NASA's greatest achievements here. Not simply building tools to survive the abyss, but building habits of thought suited to places where certainty comes slowly. The old version of exploration often imagined the unknown as something to conquer, to map quickly, to explain completely. But the bottom of the ocean resists that style. It asks instead for return, for revision, for the willingness to let a mystery remain open while the evidence gathers. That style of exploration is gentler, but stronger, and it may be the only kind that will truly work in hidden oceans beyond Earth. Because the farther we go, the less room there will be for arrogance. A machine under alien ice will be alone. Its data will be precious. Its signals may be ambiguous. Its discoveries may arrive wrapped in uncertainty. Only a science trained by places like Earth's abyss will know how to receive them well. So in the end, the bottom of the ocean gives NASA more than analogies. It gives practice. Practice in darkness, practice in delayed understanding, practice in balancing wonder with discipline, and that balance may be the real bridge between our world and the next. Tonight, we followed that bridge downward, from the open ocean into the trenches, from old machines to new ones, from sunlight-based life to life built on chemistry, from biology to geology and back again, from Earth's deepest waters to the imagined seas of distant moons. And what waited at the end was not closure, it was possibility. The possibility that life is broader than surface intuition once allowed. The possibility that oxygen, chemistry, and habitability are more complicated than our old stories suggested. The possibility that hidden worlds are among the most important worlds of all. So let the story rest there, in possibility, in pressure, in silence, in the soft, black water over the abyssal plain, and far beyond that, in the frozen dark around Jupiter and Saturn. Let the unseen oceans remain where they are for now, still sealed, still waiting, because even before we reach them, they have already begun to change us. They have changed the questions we ask, and through NASA's descent into the bottom of our own ocean, they have changed the way we imagine what may be alive in the dark. And so we come to the quiet end of the descent, not to the end of the mystery, because the mystery is still there, but to the end of this journey through it. Far below the surface, the deep ocean remains exactly as it was before we began, cold, silent, pressurized, ancient. Its trenches still folding through the seafloor, its vents still breathing heat into black water, its seeps still feeding life in darkness, its nodules still resting across the abyssal plain, holding inside them questions science has only just begun to ask. That is the strange comfort of the deep. It does not need us in order to continue. It does not pause when we stop looking. It goes on quietly, with its chemistry, its hidden ecosystems, its patient geology, and its long, unbroken darkness. And perhaps that is why it feels so powerful, because in a human world full of noise, speed, and constant explanation, the deep ocean remains something slower, something older, something that cannot be rushed into becoming simple. NASA went there to learn how to approach alien worlds, to test machines that could survive isolation, to study life where sunlight never enters, to understand how chemistry, rock, water, and pressure might shape hidden oceans beyond Earth. And in doing so, NASA found what the deep has offered every patient explorer before it. Not just answers, but a better way of asking. A better way of looking, a better way of standing inside uncertainty, without trying to crush it too quickly into certainty. That may be the deepest lesson of all. Because one day, perhaps far in the future, a machine may descend beneath the frozen skin of Europa, or drift into the buried ocean of Enceladus, or sample some dark and distant environment no human being has ever touched. And when that moment comes, the first thing it finds may not be obvious life. It may not be a creature. It may not be a dramatic sign. It may be something quieter, a pattern, a trace, a chemistry that does not behave as expected, a signal that rises softly out of darkness, the way oxygen rose in those chambers on the Pacific sea floor. And if that happens, humanity will need everything this ocean has already taught: patience, discipline, humility, the willingness to return to the data again and again until the hidden world begins, slowly, to speak. Until then, the deepest ocean remains our nearest rehearsal, our nearest hidden world, our nearest proof that darkness is not the same as emptiness. It is a place where life found other ways, where machines learned new forms of movement, where geology blurred into biology, where the oldest questions about existence began to sound a little different than they did before. Not simpler, but wider, more possible. So let the last image be gentle, a vessel floating above the Pacific at night, the surface calm, the sky dim, and far beneath it, beyond sight, beyond light, beyond all ordinary noise, the ocean floor, waiting in silence, still holding its secrets, still shaping the future of exploration, still reminding us that some of the greatest discoveries do not happen when we look at what is brightest, but when we follow the darkness carefully enough to realize it was never empty at all. And with that, we leave the deep, where it has always been, below us, around us, inside the imagination of every future journey. A black and patient world beneath the world, still breathing with unseen life, still turning human questions outward toward the stars, and still whispering, in the calmest voice it has, that the universe may be full of hidden oceans, and that hidden oceans may be full of waiting worlds. As the deep ocean grows quiet once more, and the last questions drift slowly into darkness, thank you for descending with me tonight. If this journey helped you relax, you can let the ocean carry you deeper by subscribing to the channel. And if there is another hidden world you would like to explore next, you can leave it softly in the comments below. For now, rest gently, breathe slowly, and let the darkness of the deep become still around you. Good night. A slightly longer version and now, as the deep returns to silence and the hidden waters of the world grow calm again. Thank you for being here. If you enjoy these slow, deep-sea documentaries for sleep, you can subscribe and continue these quiet descents with me. And if there is another mystery of the ocean you want to drift through next, you can leave your idea in the comments below. Until then, let your thoughts grow lighter, let the surface fade away, and let the deep carry you softly into rest. Good night, and sleep well. Best final choice for this video. And now, as the deep returns to silence and the hidden waters of the world grow calm again. Thank you for being here. If you enjoy these slow, deep-sea documentaries for sleep, you can subscribe and continue these quiet descents with me. And if there is another mystery of the ocean you want to drift through next, you can leave your idea in the comments below. Until then, let your thoughts grow lighter, let the surface fade away, and let the deep carry you softly into rest. Good night, and sleep well.